So, Ayal, let's wait one more minute, then we'll start.
Okay, sir.
So today's session is as open session, we can think. I don't have any slide, so it will be like open. You can ask your doubt, conceptual doubt, activity, or practice any doubt. You can discuss like lecture wise also. Yesterday's session.
Hello, sir.
Yeah. Hello.
I had a doubt of week 6.
Okay. Okay. So
Sir, we can also discuss, sir, inner product, sir.
so this will come under week 7. Whatever the thing will come on week 7, we'll discuss those.
Okay,
So
sir.
inner product, norm, these
Yes.
two concepts.
Okay, sir.
And yeah, yesterday Susmita had taken the class, and she have finished, I think, till affine service space
Yes, sir. Yes.
And affine mapping.
and affine mapping. Yeah. So hope it is clear to all of you who have listened this. She is very precisely and used to tell our concepts. Yeah, so let me share my screen. Let's start. Student will join slowly. So my screen is visible to everyone, right? This is everything
Yes,
is
sir.
matched.
Yes, sir.
Okay. So you can ask your doubt on if you have solved, if you watched the session yesterday session. If you solve a problem, you can ask from affine and equivalence and similarity. We will try to skip the concept regarding this affine and similarity if it's
Yes, sir. I have doubt in,
really
sir,
like it is a
activity question 7.2, question number 8.
7.2 question number 8. Just 1 minute. Somebody have asked the question, week 6 question, some activities that.
Okay. Okay, sir.
Yes, sir. So I had a lot of doubts. So is this question I can ask later?
So yeah, let's prefer to be on week 7, then we will.
Yes.
Yes.
Yes, sir.
So yeah, which activity, Sridhar?
7.2, sir, question number 8.
7.2 question number 8. Mhm. Okay, this one.
Yes, sir.
So how we are solving this?
Sir, actually, I'm not able to solve this question, sir. I don't have any approach for this question.
Okay.
Can you tell me, sir, how?
Okay,
to
so let
approach
me
this
give a
question?
hint, then you can try yourself.
Yeah.
And
Yes.
you can try here itself, and if you are not able to solve, then again we will back to the some between or in last session. We
Yes.
will try
Yes.
to solve this.
Yes, sir. Please give
So
me a hint, sir.
so we have this affine subspace from R2 to R2. It is not any from the subspace. Is a whole from whole R2 to R2, and we have some images of some vector, which is f 2 3 is equal to 3 minus 1. You can tell what is the other one if you are looking at. And f of 2, 1. Okay.
F of 2, 1.
This is
1, 2.
1, 2.
Yes, sir. F of 1,
Okay.
0. 0, 1.
1, 0 equal to 0.
Yeah. If f of minus 2, 5 is equal to a comma b,
Okay.
find the value.
So what will be then value of a plus b?
Yes. Yes.
So we have f is from f is a fine map from R2 to R2. So we know that a fine is defined like how it is. We have a fine subspace L, and let's say L prime to L prime.
Yes.
The property is the basic property. You can say property, not like how it is defined. F of I'm taking like V1 plus U. I am telling how what is V1 U. This is equal to V2 plus T of U. So L is an affine. So a affine definition of affine is, yeah, U will be a subspace and
Yes,
you added a vector,
yes, sir.
particular vector. So sorry. So this is the like definition in R2. You can say if you want to see a affine subspace. So if you want to see it geometrically, so a affine subspace in R2 is any line passing through origin. You can see. You can say. So let's say this is y is equal to minus x or x is equal to minus y something. But so this represent an affine subspace in R2. The geometric visualization of the subspace. Sorry, this is a subspace of R2. Now, if you add a vector here, let's say this is a vector v here somewhere. So if you add this vector with this affine, so our this line will be shifted to here, and this is called an affine subspace of R2.
Yes, sir.
So affine subspaces are nothing but the
Translation.
subspace added with the this transformed.
Yeah.
This is the transformed form of this line.
Yes.
So this is the affine subspace. You can say this is a simple one in R2. Similarly, in R3 are possible things like you will add a vector with the subspace. You will get a affine subspace, and this U is called the corresponding subspace. So let's say this our V is here, this V1. L is our, you can say V1 plus this U, and L prime is, let's say V2 plus this U prime. Okay. So this is our V1, and this U is a vector from U. Yeah. Okay. And this is our V2, and this U is this not U, this whole U will go to the V prime. Nah? This whole TU, sorry, this will go to the U prime. This is as the definition.
Yes.
U prime. So
f of V1 is mapping to V2.
F of V1 is mapping to V2.
L prime, and U is in U prime.
Sorry. U is our, as here U is our U. U is our. So like what is here? U is an element of this capital U, and TU will give a image. TU will be image of U prime, right?
Okay, sir.
No, not clear. Okay, just 1 minute. So what is that? The definition says f of U plus V is equal to sorry. This is the definition: V plus U is equal to some V prime plus T of U. This is the definition of affine subspace, and our T is from U to U prime. This T, right? This is the this linear transformation. Whatever will give this affine. this u is this t is from u to u prime, and our L is v plus, let's say, u, and L prime is, let's say, v prime. I'm saying here, our case here v2. If you are confusing, let's say this is v2 I am making, and again this is v1, and L prime is, this is v1 here, v2 plus u prime, and this t is from u to u prime, and this f is from L to L prime. So tu will be tu. This is a single vector, will be an element of u prime. Is it clear now?
Yes, sir. Yes, sir.
Sir,
Okay.
hello, sir. Sir, we have written v1 plus u is equal to v2 plus tu. Why not?
Tu,
Yeah, why not we have written v2 is equal to f v1 here?
v2 is equal to f v1.
V1.
So actually, yeah, you can say that also. So yeah, if you want to, that's the if you want to make it like this, this is no issue. You can make it
Okay.
like this, or whatever you are assuming the image. So let's say this is v2. I'm not saying anything. Let's say this is v2.
V2.
Okay. So that's
Image of
why
V1.
whatever is image, let's assume that this is v2. Whatever you are getting in image, let's assume this is v2.
Okay.
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 Whatever the image. Yes. So our f is from L to L prime. L is, our case is here R2, and here is R2 also the same. So assume our V is this. V1 is 0. To solve this problem, I am assuming here, let's say V1 is 0, because this L is whole R2. So 0 means 0 vector. 0 means I'm to say 0 vector. Suppose this is 0, so this will be f of u is equal to v2 plus tu. So if you want to make it f of 0, 0, no issue, you can make it. So for simplicity, make like if to solve it or to write quickly, let's assume this is v2. I think there is no issue with writing like this. If you want to write like this 0, 0, you can make it. Otherwise, no issue. Okay.
Okay, sir.
So this is okay. So this is v2. Assume this is v2. So we got this f of fu is equal to v2 plus tu. So we have, so u is our from this this u is from our corresponding subspace. The corresponding subspace here is also the same R2. L is also same, means corresponding, and the affine are the same R2 itself, right here. So whatever the images here he is given, you can substitute here. Like f of, assume this is 2, u is this one. So f of 2, 3 is equal to, let's say this is v plus t of 2, 3. This is t here. We have whatever the images, and this is equal to, we have already 3 minus 1. As the definition is given, we are totally going to like that. Till here, Sridhar is clear?
Yes, sir.
But it is clear to all of you what I'm writing here?
Yes, sir.
Okay.
So 2, 3 is a subspace, no, sir? 2, 3.
2, 3 is an element of subspace, correct?
Subspace.
So in our case, what is the subspace for this L prime? The same R2 itself, right? Because R2 is itself subspace. I are saying 2 as a affine also. That's why it's working. Clear?
Okay.
Our L is R2, and what is the corresponding subspace for this L? R2 itself. U is our R2 itself also, right? Because that is a subspace. R2 is not a subspace, vector space, total vector space. So
But sir, we
L
have
is
always
actually
taken.
how it is. What is
Okay,
our
sir.
L is here? 0, 0 plus
Yeah.
R2 case kind of. Clear?
0,
Now?
0 plus R.
Yes. Clear now?
Yeah.
So that's
Sir,
why it's happening.
Excuse me, sir.
Hmm.
After that, we are going to find the expression for t.
After that, we are trying to find the expression for t.
Then
If
we
we
will
once we will find, then
Yeah.
what is f again? We substitute here as here. whatever we are doing, or on this equation, and easily can get. So actually exact t, the main,
And for that
because
reason
of t we are able to.
we are assuming that this v is 0 0.
That is correct. Because of that we are assuming v as 0 0.
If we don't assume it to be 0 0, then will
So
we be able to find the expression?
it will be difficult. Then here the equation, making the equation, it will be difficult.
So every time this type of question will come, we will assume this one to be 0, and
because
then we'll find
correct,
the
because we are
expression.
assuming here our, you can see that our v is here also 0 0 because of this reason also. Our v l is our like 0 0 plus r2. That's why, or sorry, v1 you want to say. So actually not only the reason is here. I forgot to tell you, because of this reason our v1 is like this. Okay, this v1 is actually 0 0. That's why it's happening.
Yes, please carry on.
Yeah.
Sir, is V2 also 0 0?
Not necessary. Whatever the image will give of 0 0, that we will calculate. No, it is not necessary it will be 0 0. That's why I want to find exact mapping. That's why you want to find exact this f, how f is mapped. So f is
But if L
actually, we
is
want to find
R2,
f.
but if L is R2, then that V1 must be 0 0.
Yes, correct.
But if L
No,
prime is
not must be v1. It can be separate also. Not only this 0 0, it can be different. You can write like this also. This will also still give the same, right?
Yes, sir. This will
it will
also
still
give
give
the
R2.
affine
So, but
subspace.
for the simplicity, I just made it 0 0. Okay. So now next is here. What is the image? 3 something. What is that? 2 1. So we have image is 1. So f of, let's say, 2 1 is equal to again v2 plus t of 2 1, and is image is here, image of
1 2.
this one. So again the next one is, I think, this is 1 0. F of 1 0 equal to v2 plus t of 1 0. This image of 1 0 is
0 1.
So 0 1. So we have 3 equations, and you have to solve. Like, we have what we don't know, forget about this one. So actually we want to try to find this 2 and t. What is the image of t2 3, what is the image of 2 1, like this. So we have 3 equations and we want to solve this. So how we can solve? Like, assume this is 1, this is 2. This is actually a good question to understand the whole affine services, what is happening, and also what is here for the linear transformation. So you can make it like 2 minus 1. This equation is 1. You can subtract it. So you will get what you will get. This t of, or
2,
t of 2 3 minus t of 2 1 equal to 3 minus 1 minus 1 2. This you will get. So use property here. This will give inside will go. It will give the one vector because
Yes,
of
sir.
the
We will
linear
go.
property.
1 comma
It will
2.
be 0 and it is 2.
Sir,
And this is equal to.
this is 2. Yeah.
2.
This is 0 comma 2.
Is that 2 comma minus 3? Na?
Minus 3. Yeah. Yes.
Now again 2. You can do 2 minus 3 something. So we have this one. So again t of, you can subtract here. So it will be 1 and 1. Yes. And again you can subtract this one with this. So it will be 1 and 1. Is it correct? What I calculation, please check my calculation. So I'm subtracting here t to my t 2 comma 1 1 0.
Yeah,
so it will
it's
give
correct,
1
sir.
and
It's
1.
correct, sir.
Yeah.
Okay.
Yeah.
So we have two images we got. T of 1 1 is equal to 1 1 and T of 0 2 equal to 2 comma minus 3.
Yes.
And now you can check that this is this vector and this vector is actually forms a basis of R2. This one, this 1 1 and 0 2
Yes, sir.
forms a basis of R2. So that what it means that any vector, if you take any vector from R2, I am
Can
taking
be
any
written
vector, let's
as
say
a
xy.
linear
It can be
combination of.
written as linear combination of alpha time, let's say assuming 1
Yes, sir.
plus beta time 0 2. This is the mean of, this is the use of this vector, any vector, this is any vector written as the linear combination of the basis element. So this is xy is equal to, we want to actually try to find the x alpha and beta. So this is alpha and this is alpha plus 2 beta. So this implies alpha is equal to x and alpha plus 2 beta is equal to y. So this implies alpha we have x, so 2 beta is equal to y minus x, beta is equal to 1 by 2 y minus x. So we have xy is equal to x 1 1 plus 1 by 2 y minus x 0. So you know that how to you know already why I am doing these all, because once you have the images of basis element, you can find the expression, whole expression T.
Yeah, yes, sir.
So now apply both side T. Apply means what is the image of, you can get now T of xy is equal to, this is work as a scalar, xy are scalars. So x, now T of 1 1, T of 1 by 2, this is work as a scalar here out, T of 0 2, and we have the images of this one.
Yes.
That's why we are trying to reach like this. So this is x, T of 1 1 is 1 1 and plus 1 by 2 y minus x, T of 0 2 is 2 minus 3. So here you can do, or you can make it like in a proper okay, let's solve it and then it will be, so it is x and plus y minus x, and this is x plus minus, it will be minus 3 by 2 y minus x. So this will cancel at y comma, this is, these all are in single vector. This expression tells a single vector. This is y here and this is 2 3, what it will be, what is the expression here, 3x 2 minus x by 2, or you can leave it here as it is, minus 3 by 2 minus x. So this is, we have the expression. Now actually exactly if you want to try to find f, so we have to find this v2 also. So we have already so many things, like we have expression this one, use this expression, you can easily use this expression, and T of 2 3 we can find the value from the expression and send it to this side, we can find v2. Now once you find v2, then done. So we can find, so that is here of, what is here 2 3, or to more to skip the calculation, let's use this one, because this is here 1 0, easily we can, again you can find the image from the expression and send it to this side. So T of 1 0, let's say 1 0 is 0 here, and this is 1 minus 3 by 2, it will become plus. So this is plus 0 and 5 by 2. Is it correct? 1 and this is 0 and this is plus, it will become plus. Okay,
Sir, we are trying to find out the value of V2 now.
v2, yes, from here this expression. Once we find, then we have this one, for any vector we have this one, v means u equal to this, f of u is equal to v2 plus t of u. We have this expression, so we can put here -2 5 our expression, this is equal to v2. Once we found here -2 5 also we got, so whatever we got here, just substitute an exact value, you can find AP. So can I leave here what I mean to say? You can solve easily now.
Yes, sir.
So is it clear to all of you? If you have doubt, again I will repeat and tell you what is happening here.
It will be helpful if you could repeat it, at least the major steps once, please. I joined about 5 minutes late.
So then I will say, if you are not understood, then okay, I can repeat. But if you join late, then you can
Not the
rewatch again,
entire thing.
because I very slowly I taught everything very slowly. If you are not didn't take step, then okay, I will repeat again. Otherwise, if you come late, then I will say you can rewatch again.
Okay, no problem.
Each step I slowly I tell you. I told here. Okay. So that's all for this affine, I think so. I hope it's made clear to what is affine, what is affine linear map. Here I told you one by one what is affine mean.
Sir,
In the geometric mean also.
sir,
And
sir, F parts,
okay.
I have served out. 3 comma -1 is equal to F. Where you have written 3 comma -1 is equal to F.
Actually,
2
this is
3.
so this is the
Yeah,
just
yeah.
mapping. Whatever we have, this one. So just this side, first I wrote that this image, this map. So we have evaluate this 3 comma -1. This is exactly whatever from this expression we are writing. T2 plus T23. Just rearrangement that this side. That's why I just wrote to understand exactly. Clear what I am saying? Is it clear?
Okay.
Okay, so this is from affine. So let's move on to our
Yes, sir.
let me
Inner
show you
product, sir.
Inner product, length and angle, and inner product. So in between you can stop me, and if you have previous doubt, means on week 7 conceptual, please stop me. Otherwise I'll continue with the length and inner product. If you have doubt, if you are, and again we can discuss those, and back to again this length and inner product. Okay, so length and inner product, as you know, here for this term is very similar, or you can say not exact, I will say, but very similar to as you gone through in maths one. The same word, why we are doing this, let me tell you why this is the very similar to this one. Because of the word, there is dot product,
Yes.
and you know the Euclidean norm.
Finding
you know
length is
Euclidean.
easy, sir, but this inner product part is quite difficult, sir, I think.
Okay. So
how we are getting that, sir?
Okay. So as in maths one, you know that this is not called R2. This is called coordinate system in maths one. You know, this is coordinate system. This is x-axis. This is y-axis. This is called point on xy plane kind of thing. Let's say this is 1 2 or whatever, and you have another point. This is 2 3, or this is 3 3 something. So what is the distance between these two points. So you know that formula is x minus or whatever the 3 minus 1 whole square plus whatever the formula is, you know, this is AB and this is CD. Same thing is here also. The term is now changed. This is called the length of a vector for what purpose? Suppose somewhere is, let's say this is a vector here AB. Let's say this is a vector here AB. So length of a vector is exactly, we will use the same formula. So as this is kind of a minus 0 square plus the same as in math 1 you did. So same here, the same thing is here. The term is now changed, a square plus b square. If you know that a minus 0 whole square plus b minus 0 something, sorry, whole square root over. This is derived from here, the same thing. Why? Because this is only the term why I needed to change here is because of this dot word to make more generalized form. See, this is a specific thing. This is a kind of a specific playing to in xy plane, but we want to make it more generalized. That's why the concept came inner product or dot product or this length or other things. Like you know that in maths 1 it is another thing, angle. Yeah, angle between two lines, something is that. The same is here in R2, sorry, in vector space. In vector space we are saying this is a vector space, and if you do as usual means you R2 means R2 is a vector space with usual addition and scalar multiplication. This makes more easier, more whatever you studied in math 1, math 1 in the sense make more convincing or very similar to working as a xy plane. That's why usual word added means usual addition and usual scalar multiplication. So length is, let me go with the video, it will be more better. Then we will go to the inner product and now. So dot product is actually a specific inner product. And this is mostly work in the R2, R3. We just gave the name, not we means this book or this concept gave the name as dot.
So dot product works in Rn.
So dot product is work is, yeah, that's word is given. So let's go. Let me tell you, if you have Rn and you have a vector, let's say a1, b1, c1, or maybe a1, a2, an, another vector b1, b1, sorry, b1 to bn. This is a two vector from Rn to from Rn. So dot product between these two is just multiplying the coordinate wise. That's all. This is the,
And
but
adding.
in the inner product form, if you want to write, it will be written like this. The word is just changed here. Because why this is this kind of angle bracket? Why it is given? So if you say this angle is, this inner product is dot product, so this is just the same as a1 b1 plus a2 b2, like this, whatever the definition. If you are not saying this is dot product, so you have to give the definition of this inner product. So okay, so whatever the thing, maybe I just jumped the here. Let me back to the same place. So I hope, is it clear what is angle? This is just a formula, and sir is also taught very well what is angle between two vectors, what is the length of a vector. So we can skip actually this video. The main thing is this video is actually a specific form of this, the fourth one. inner product and norm. This is worked on the dot product. That's why it's look like very simple as in maths 1. It's look like as in maths 1. But this specific thing, this video is a specific thing of this inner product. I will tell you what is the reason. Okay.
Yes, sir.
So what I told here, whatever, is it clear to all of you? No?
Sir, we
Maybe.
can skip this length and angles and move on to the inner product.
So maybe
we
it's
can.
better to first see this one, then back to see this one, because this is a specific thing of this inner product and norm. So actually, length is one type of norm. Dot product is as one type of inner product. That's why I'm saying a specific thing. Length is a one type of norm. Dot product is one type of inner product. So here is the definition for inner product. So let me show you all the definition. Definition in means condition. These are called the condition. So what is that here? You suppose if you have a vector space. Let me make it more generalized form. If you have a vector space, you know that if you have a set and satisfying those all 8 properties, then we can say that set is a vector space.
Yes, sir.
Now, if you have this vector space, so let's define a function. Function is how it is. The function is, see, this vector means vector space means this is a vector from the vector space. So suppose if v is equal to r2, so a vector in r2 will be like this coordinate kind of, this first coordinate, second coordinate. So this is a vector space. Suppose this is a vector space, and now we define a function. Function is like this. This is the kind of, you can say this is f. This is just a notation like this. This is just a notation. You can denote it like f also, no matter. But this is just a notation from v cross v2 real number. So how it is defined, like if you want to say, if you want to make it change here, so this is, suppose this is a function and from v cross v2 r. So can you tell me, if I just wrote here this kind of, so how it will be look like in the form of like this? How it will be look like here? Means take a vector v1, and this is from v cross v, means take two vector v1 and v2. So it will be like this: v1, v2. There will be a relation between v1 v2 which give a real number. Let's say this alpha, any real number. So if you change it this here with this angle kind of, so it will be look very easily like this is. Now if you change this here with the angle, so it will be v1, this is v2. This function give a real number.
Sir, how will we come to know what is the relation between?
So now what is the relation? Then sorry, let me mute to all. So once you have this, so now the question is how we define. So suppose you have somebody's wrote like this, so surely he will give function how it is defined. No, if somebody is give you, he will surely give the expression also. Okay, this function is defined like this. So let's see from the activity, because this time I haven't remember any inner product. Okay, so see again, the first activity question is the same, change with the angle kind of notation with the f. It is also, and it is also an inner product or not, we will check this. So he see how it is the define f from v cross v2 real number r. Okay, this is the v is subset of r2. how it is defined? F of VW, as just now I wrote V1, V2 equal to, he gave the exact notation. This, how it is defined. Let's discuss this one. So there we have a V F from V cross V to R, such that F of VW equal to, so our V is from V and W from this V, and V equal to V1, as here he is given V1, V2, and W is equal to W1, W2. He just given, because this is subset, this V is subset of R2. He just said this V is a subset of R2. So it will be in coordinate wise. So this is V1, V2, and W is equal to W1, W2. And now he gave the relation between this is in this form. He gave the relation how it is 2v1 w1 plus 5v2 w2. 2v1 w1 plus 5v2 w2. So let's see with an example. Let's say v equal to 1 2 and w is equal to, let's say, 2 5. So f of 1 2 comma 2 5, this is equal to, this is our v1, this is our v2, this is w1, this is w2. 2 times v1 is 1 and w1 is 2, plus 5 times v2 is our 2 and 5 is our w2. So this is 4 plus 25 50. So this is exactly equal to 54. So see that this is a real number. So see that how it is defined from a vector space with the different kind of notation v cross v, like this is a form of vector, 2 vector, and the function, see that function is how we got a real number. Now we have this function. So once somebody gave the function, so what is that? Again, let's go with one by one. So suppose somebody says we have a function from v cross v to R, okay, where v is a vector space and defined like this. V is a subspace of R2, he just said. Okay, so the R2 means vectors will be in coordinate wise, as here we just took the example and see that. So if we have this function, okay, is it clear to all of you what I am talking here?
Yes, sir.
Okay. Sir,
so once
we can
you have
call this inner product to this one, which you just solved.
So now when we call, so once you have a function, so if you have a function, if this function satisfy, okay, let me change with the notation also. So let's change this f with the notation, this angle kind of. So you can change it v comma w equal to v1 w1 plus 5 v2 w2.
Sir,
Now
so this,
I think you don't have problem with this angle kind of thing. You can change with f or this angle word, this angle notation. Now you can continue. Sorry, I just interrupted.
sir, it's okay. I was just asking about that notation only. So I was asking, so that is called angle.
Angle bracket, not angle bracket.
Okay, angle braces, right? Okay. So we can use it for real number also. It's not like a degree kind of thing.
No,
like,
this is not a degree like here.
No,
It
yeah.
is called an angle bracket.
Okay, got it. Thank you, sir. Yeah, continue.
Okay, so I now I hope with the f and this angle bracket, it will not create any problem. This is just a notation of a function. Okay, now once you have this, so if you have a function defined like this, okay, somebody's given said that, okay, this one, the function is defined like this. If this function satisfies these 4 properties here, then this function, just call it name as a inner product. That's all. If this function satisfies this 4 property, you can call it this function as a inner product.
Inner product. Yeah.
if
And
that function not satisfy any one of the property,
yes,
any one of the condition, property, let's better to condition. If you any one of the condition, then you will never call it as a inner product.
and dot product satisfies all this property.
And dot product is one kind of inner product which satisfies all these properties.
Yeah.
So let's see that how we will check. So we have this example. Okay, so let me better to tell you something name is here. So I will, okay, I'm writing here and one by one tell the
Sir,
name.
dot product is not derived from there. Dot product satisfies all that property. That's why we are calling it as an inner product.
Inner product, yeah.
What
You
I
can say
understood,
otherwise,
sir, what I understood from the lecture that dot product is derived from inner product.
actually dot product is derived, yeah, derived from inner product. See, once you have something like if you are able to reach somewhere, then once you reach that place, you will see around that. So like what is that? Once we found the property in R2, R3, we have some property like a dot product. Once that okay, we are doing like this and we got something. So we want to try it more generalized form. That's why the concept come inner product. What is the thing is once somebody, some mathematician got the inner product word and he just want to make it more generalized form. That's why he make the concept inner product, some concept, and studied ahead something more generalized form. So one inner product, and just he said okay, inner product is an example, sorry, dot product is an example of inner product. We have more generalized form. So generalized form means like this. We the inner product says only this one, no?
Yes, sir. We can
V1,
define
let's
any
say
function if v and
VW.
w.
So it is only like this, V1W1 plus V2W2. The dot product is exactly the definition, multiplication with the coordinate wise. But the generalized form is not only the multiplication, we can multiply with some scalar also. So actually this function is an inner product. We will check this. This function is an inner product. So once we have this function, so the conditions for to form an inner product for a function. Let's say I'm again in the more book, how the book is written, or sir have put this chart. So if this property hold, first property, this is let's say V, and okay, suppose we have a function, and I don't know how it is defined. I don't have any idea how it is defined, but we have, let's say V, U, and W vectors from this V, and this function have this property is greater or equal to 0, and if V comma V, this inner product is 0, this implies this V equal to 0. Okay, this is called the positivity of this inner product. If you want to give it name,
Yes,
this is called the positivity or positivity something name. So this is called the positivity, but if you don't, you will not see some, this word is not used in this activity. Something is positivity condition. Sorry, here is name. So this is called positivity condition. The second property of this function is, property means if it will satisfy this function, this V plus U comma W equal to V comma W plus U comma W. If it satisfies this one, so it should satisfy this one. This is the another condition. This is called the linearity. It's called linearity condition. Let's see that here. The word is not only linearity. Actually, this is bilinearity. What is more proper way to say? Actually, why this bilinear term? I will tell you why this bilinear word is used here. See, where is video? So actually this inner product, if you replace this real number with the complex, or your vector space is not only over R, this is on the complex field also. R is a real field. If you change in complex, then uh, the scenario is totally different. The whole definition will be changed here. Mainly this one, these two. Sorry, for this one. Mainly this one will change. This one and this one. But our case here only we are studying on real number. That's why only need to concentrate whatever the properties here. So bilinear properties actually says, see, bilinear means this is linearly expanded here. If you change it here like this, see this one is, okay, let me connect with the fourth definition, then you will say why this linearly change with the word bilinear, or you can say bilinear also. The third one condition is v and w. If you have, it can be w and v, means commutative here is called, this is called symmetricity. Like if you have these two vectors, this one, if you change the position, as here you have this one, okay, you have this first one, this 1 2, and this 2 5. If you change the position first 2 5 and then 1 2, still it will give the same this value. So if the function satisfy this property also, okay. And the fourth one is c times v and w equal to, c will be out here and vw. This is called okay, I will tell the name. This is called the symmetricity. And bilinear is why this is bilinear. You can say this is the expanded on the first place. If you change this w, v plus u, okay. So if you change the place here, so because of this property, it will be this one. Because of this property, it will be back to the same place. So again, the expression is the, you can say you will get the same here. So means it is working as a linearly both side. So that's why the word is written here bilinear term. Bilinear. This is the property of bilinearity. You can say bilinearity condition. And the fourth one is something named. This is scalar something. What is the name? You can see activity have something written. Positivity, bilinear, and symmetricity. This word also came for linearity itself. Also comes as under the linearity condition, means bilinearity condition. So if suppose you have if you have a function like this, and this function satisfies these four conditions, then that function just name it as this. Okay, this function is an inner product on this vector space V. So let's see our case here. It is more will tell you the main thing, like whatever we just know the, okay, this is called inner product. So let's see the use of this with an example. So we have, again I am writing with this angle bracket kind of. So this is a vector space. Sorry, this is a function from R2. Sorry, this is R. This vector space is subspace of R2, and this function is defined like VW, where our V is V1, V2, and W is equal to W1, W2 with 2V1, W1 plus 5V2, W2. So is this function is an inner product on on vector space V? This is the question. So till now, whatever I discussed, is it clear to all of you? Am I audible? Am I audible?
Yeah,
Yes,
yes,
sir.
yes, sir. You
Or
are.
it's boring, or I don't know. Is it clear to all of you, or still
Yes,
you
sir.
can stop me again? I will repeat it here.
Yes, sir, it's clear.
Yes.
Okay, so let's see. It will be more clear when we will solve this example.
Correct.
Okay,
Yeah.
so we have this example. Okay, this angle and the function is defined like this. So is this function is an inner product on this vector space or not? This is the question. So let's do that. So the first condition is VV should be greater or equal to 0, and if VV, this inner product, is equal to 0, this implies this V equal to 0. Okay, so let's our the case is here. So let's say V is our as we assumed V1 plus V2, sorry, V1 and V2. This is our V. So just substitute here. Okay, V1 VV. Assume take the left side. Okay. Now this VV means angle V1 V2 comma V1 V2. This is the same. Okay. Just taking VV kind of thing. So this is how it is defined: 2V1 V1 plus 5 V2. V2 you will get this, multiply this with 2 times, this multiply with this 5 times. So you got this V1 square plus 5 V2 square, right? Now you know that this both are square kind of thing. So whatever you will get for any, if you change this V with 1, 2 or any vector, it will always be positive. That means it says it is always greater than 0, greater or equal to 0. And once you assume, okay, let's assume that, okay, this is equal to 0. This V1 square plus 5 V2 is equal to 0. What it means that? It says V1 is equal to 0 and V2 is equal to 0. Then it will be 0, no? Because both are positive. So when this equal to 0 means V1 is equal to 0, V2 is equal to 0. Means what? V1 V0 means our V is exactly 0, 0. So as here the first condition.
Sir, could you
Okay,
repeat the
positivity,
last
okay.
part? The last part.
Okay, the last part is, see, this is greater or equal to, or maybe it is, if V1 V2 non-zero, then it is always greater than 0 for any V1 V2.
Yes.
Okay, suppose V1 this is equal to 0. If you assume this is equal to 0, when this term will 0, when V1 is equal to 0 and V2 is equal to 0, because both are positive terms.
Yes.
This is V equal to 0, V1, and V2 0. And V1 V2, what are the V1 V2? V1 or V2 are the coordinates of this V. No,
Yes.
these are the coordinates of V, means says V equal to 0.
Yes.
So this
Okay.
this satisfies
So it
the
satisfied the first condition.
first condition.
Yes, sir.
Positive.
Okay, positive, it is always positive for any V, and if it is 0, then V equal to 0.
Right.
Actually, remain to the reverse part. Remain to, see, you assumed 0 and you got 0. Remain to, because here is the if and only if condition is written here. This is called if and only condition. If and only, reverse back means assume, okay, V equal to 0. Okay, this implies V1 is equal to 0 and V2 is equal to 0, right? Or V is V1 V2. So this says, okay, put the value, this VV equal to 0 0 0 0, and this is equal to 2 times 0 plus 5 times 0 means 0. So means this condition holds if and only. I mean to say this condition holds if and only condition holds for both sides. If you assume this is 0, you got 0. If you assume V equal to 0, then you got this one. Okay, inner product is 0. So as here, if I assumed, okay, this is 0, we got V0. If you assume, okay, V0, we got inner product is 0. So this is a if and only condition we checked actually. So here is actually 3 conditions if you see clearly: positivity, and once you assume 0, you got 0, and reverse back also. In single condition, you have 3 conditions, which always you have to always check this one. And mostly this will be, if you have function, this will very much help you to make, okay, this will be a inner product or not. Like suppose you have a function, so check these conditions. This is very much make helpful to clarify that this function will be inner product or not. And then check this one, and then check linearity. This will also help. This is a very important to check a linear this function is a linear or not. First check this one, then like if you want to make it preference, this first check this one,
Sir,
then this one, then this. You can say.
sir, how will we check linearity in this question?
So let's we just discussed the first condition. Now let's check the second condition. Second condition is like this. Okay, so we have v equal to v1 v2, w equal to w1 w2, so, and assume u equal to u1 u2. Okay, so substitute here. So this is this is v1 v2 plus u is our u1 u2. Okay, and w is our w1 w2. Okay, now this is a single vector just added with plus sign, so this will be v1 plus u1, and
So you are assuming u1 u2.
I'm assuming u1 u2. U is equal to u1 u2. I just assumed here.
Okay, sir.
And this is v2 plus u2. Okay, I will make it more precisely. This is my v and this is my u, like this only. So it is like this, or maybe like this. If it is black, then it is v, or this is my v, and if it is like this, then it is u. So okay, so this is w1, this is w2 here. Okay, so we have one vector, we have another vector, and how it is defined? 2 times this is our one vector, 2 times v1 is our this one, v1 is our means over here, this as here is defined, this case, this is for our case. So 2 times sorry, v1 means our this here, this inside portion, this is a whole bracket, this inside portion. So 2 times v1, sorry, this v1 plus u2, and multiply this one, multiply with this one multiply with this one as definition of inner product of this function, and multiply with this w1 plus 5 times this one multiplied with this one. So this is v2 plus u2, and this w2. So we have 2 v1 w1 plus 2 u2 w1 plus 5 v2 w2 plus 5 u2. Oh, sorry, I made here mistake. u1 and this is sorry, v1 and this is u1. This is added with this one. No? I made it here mistake. This is u1 and this is added with this one, adding these two vectors. Okay, and the definition of inner product is as here. This one multiplied with this one multiplied with this one 5 times. So this one and this one here, we got this expression. So what we have, we uses this one, this is this one, this line, after this line we can simplify, we can get, we got this one, after simplification we got this one, and now this one. Now let's check that. Okay, the definition said it should be like this, v w plus u w. So what I did here, I checked the left side, remain to check right side.
Sir, I'm not able to understand this this one, v1 plus u1 comma v.
Okay. Okay, so let me, maybe because of more, okay, let me write again. Let me. So what I am doing here, or maybe in next line, the condition is, the second condition is like this, v u w equal to this one, v w plus u w. This is the second condition. Our v is v1 v2. I assumed, okay, u is, let's assume u1 u2, and W is already we have assumed W and W2. So we have this equation. We want to check is this satisfied or not with this, whatever the definition for this angle bracket. Angle bracket means function, for our function is satisfying or not. So let's take left hand side of this, which is this one, the whole. This is the left hand side of this equation. So
Yes,
left
sir.
hand side is says V U W. So let's simplify it. Let's substitute the value of V. V is our V1, V2. U is our plus U1, U2. And W is our W1, W2. Okay. This is the, as left side is just substituted the V1, V2, W, W2.
Sir, we can write this as a single vector.
So these two, there are two vectors. So add these two vectors. This will be a single vector. This is, so this single vector will be V1 plus U1, V2 plus U2. This is a single vector. Another vector is W1, W2. Now, how our function, this function is defined? It is defined. Let me write again here the function. Let's say our function is defined V1, V2, W1, W2. This is defined 2 times V1, W1 plus 5 times V2, W2. So means multiply here, this one is multiply this one, this one is multiply with this one. The same here.
Yes.
This is the first coordinate.
Yeah.
This will multiply with this one, and this will be multiplied with this one. So
Okay,
this is
got it.
multiplied with this 2 times V1 plus U1. This multiplied with this one, W1 plus 5 times this vector, as here. This is multiplied with this one. So this is multiplied with this one. So 5 V2 plus U2 and multiplied with the W2. So you have this expression. So whatever the expression, we can later see, or you can directly open here. This is same. So we took, this is left side. Now let's find for right hand side. So right hand side is this one of this equation. So this is angle bracket VW plus UW. So let's substitute here. V is our V1, V2, W is our W1, W2 plus U is our U1, U2, U1, U2. This is V1, this is V2, and W1, W2 is here. So how this function is defined? This is multiplied with this one. Here is not square.
2V1, W1.
This is multiplied with this one. This is multiplied with this one. This is 2 V1 W1 plus 5 V2 W2 plus, here is plus again, this U1, not 2 U1 W1 plus 5 U2 W2. So you got this one, this expression. Now if you simplify this expression, you can see that this is 2 V1 W1 plus 2 U1 W1. This is, just open the bracket here, open the bracket, this one, 5 times V2 W2 plus 5 times U2 W2. See that this one is here. You can check that this one is somewhere, this one here, this is here, this is here. What is here, that what it mean that, okay, this equation is satisfied with this, whatever we assume for the general case.
Yeah.
So That means our second condition for this function is satisfied.
What is this condition called? Bilinearity. Is it the one
This
you
is
are
called
saying?
bilinear condition.
Okay.
Now let's check for the third condition. Third condition, what is this third condition? This is called symmetricity. V W should be. This should be like this. So I think it is very easy to. This is just a definition, and actually this will be the same. The reason
Yes,
is
sir.
just multiplying the scalars here. Scalar means real number. So it's not a real number multiplying the real number, or you can say scalar. So this is very easy to see it. And the fourth one is CV time W. This C will be out with this VW. So how it will be? Let's see that. So okay, C is here any real number, means any scalar here. C is our scalar, and V is a vector. W is a vector. C V is our V1 V2, and W is our W1 W2. Okay, so we have this equation. This is the left hand side. Okay, now let's solve it. This is equal to CV1 CV2, multiply the scalar with the vector, then as the definition is here, now this is multiply with this one is multiply with this one, so 2 times CV1 W1 plus 5 times CV2 W2. We have this expression. Now let's take the right side. LHS karna L right hand side, not L, right hand side, left hand side.
Yes.
I really L, sorry. This is yes here. This is yes. Okay. So this is now take right hand side. This is C time. Our V is V1 V2, and W is our W1 W2. Okay. So C is our multiplied with here. Let's open the first function. This function we just denoted with the angle. Okay, the function is defined like this multiplied with this one multiplied with this one. So 2 times V1 W1 plus 5 times V2 W2. Okay. Now this is an scalar. These are the multiplication of real number. This is a real number. This is a real number. This is a real number. So 2C V1 W1 plus 5C V2 W2. Match the expression with this one. You got right hand side is equal to left hand side. Okay, the fourth condition is satisfied. Here is the also left hand side equal to right hand side. So you
Sir.
see that.
Sir, for inner product, condition is always given, sir. Without
condition is
we
always
cannot-
given. You have to
Okay.
check. You have you in a question like as here.
Question.
Question is you have question and you have
Yeah.
the here written the condition. Which condition is satisfied? As here. This is the function you have. See now the angle word here is notation also change. Angle with the function f. And you
Function
have
is
this
given.
expression.
Oh.
So function is given. You have given inner product. You have to check okay, symmetricity satisfied, bilinearity, positivity, whatever what is satisfying here.
Oh.
Sir, only this type of question can be made from this concept.
For this from this week, because you will see in the week 8, we'll see now once you got the definition or got some inner product.
Yes.
This will use somewhere, no? So you will see the use of in week 8. What is in week 8? Gram-Schmidt process, orthogonalization. If you will see one by one, it will be clear once you got what is the inner product means.
Sir, just look at question 3, option 3.
Here.
Yeah, I mean all these, I don't know. Yeah.
Okay, so let's finish this. Then I will back to the norm. This is called the sign of norm.
Yeah,
Norm
norms
is
and
also one
norm.
kind of function.
Yes.
Okay, so once we will reach, maybe I will discuss with this example as here I discuss with this example. Okay, so hope what is inner product, when we call a function as a inner product.
Yes.
And how we will check, is it clear to all of you?
Yes.
Yes, sir. We can move toward next.
Okay, so next is what is after this video? Just 1 minute. Okay, so here is also so dot product is now sir is solving how the dot product is an inner product. So yeah, actually we discussed with the term also dot product. So dot product is just now I told you dot product is an specific kind of like how it is the given somewhere I just wrote also dot product. Okay, so dot product is the same with it will be not here 2, it will not here 2 and 5. Dot product is in saying to be dot product on a vector space in it is mostly in R2 and R3. Okay, so dot product is specifically for R2 and R3, means R2 means Rn for Rn. So I am audible, no?
Yes, sir.
Okay, so dot product is especially on the vector space Rn. So it is defined like v1 w1 plus v2 w2. So the reason is here.
May I request something? Can you
Sorry, yeah.
could you please write it on the next sheet, which is more clear?
So actually, why I'm writing here because of this one, relating to this one. So as here the specific thing is given that here is multiplied with 2 and 5, but our main dot product for any Rn, if dot product, let's say in Rn, the dot product is defined like this. Let's say v equal to v1 vn, this is a vector, and w is another vector, w1 wn. So if you want to notate it like this, so this is okay. I'm making a proper notation also. Dot product. If you want to make it notation, it is like this. The general case is also as in similar, but the definition of this function dot product is also a function which is from Rn to R. Sorry, this Rn across Rn to R. And if you want to notate it here like this, no matter how I'm notating it, so this is v w and defined like coordinate wise multiplication. So this is v1 w1 plus v2 w2 plus vn wn. So, and anything remain, what is here, something is remain, I think, v1 w1. Okay, this is dot product. So if in notation wise, as what is the notation, it is actually also can be notated as v dot w. This was remain from my side. So it is like this, or maybe like this, v1 dot dot vn, here is dot, and this w1 wn. So this, if you want to notate it like with this angle bracket, this is vw kind of, And this is actually just multiplying with the coordinate wise. V1, W1 as here. Vn, Wn. This is called dot product. And this dot product is actually specified on Rn. N can be changed from 1 to 2, any finite number. So you can check that whatever the definition is here, you can check that this definition of this function, the definition dot product, this function is actually satisfied with these 4 conditions. It will satisfy all 4 conditions. So that's why this dot product is an inner product on the vector space, whatever vector we are taking. A vector space means R1, R2, R3, whatever. Okay, so yeah, that's the I want to tell you. And yeah, so yeah, sir is proving here how the dot product is an inner product. You can see one by one. I just wrote the definition of dot product. Here is dot is given and how it is a positivity condition. That's all he proved. The next is next example is took this one. It is defined like this. And proving, okay, so what is here happening? This is you can say additional thing. This is an additional thing. Sir is saying this thing can be written as the matrix multiplication. This expression, there is nothing. This is a, you can think as an additional thing, because our main purpose is the function is defined like this. We want to say, okay, this function is an inner product or not. This is an additional information that this expression can be written as in this form, matrix multiplication form. That's all. This is the sir is only saying whatever the sir is also multiplied and says, okay, you got this expression. So this is an additional thing you can connect. And next word is the norm. So is it clear to what I just told you in the video, connecting with the video? Is it clear to all of you? Am I audible? Okay.
Yeah, yes, sir.
Okay. Okay. So next is definition is norm. So again, norm, the word here length. It is induced, norm word is induced, you can say, from the length word. Somebody is in mathematics, like somebody is okay, want to what is how the norm word came? Not possibly, but just I'm thinking also maybe it came because of this one. We suppose you have a vector here and he want to connect, okay, this is a vector AB, so what is the length of this vector? So he just connected, okay, this in plane R2, so it will be like A minus 0 plus B minus 0. So okay, just said, okay, this is the length of this vector. So once he got this, okay, this is the length of vector, he just generalized the word length with the norm word. So norm actually word for the measuring the vector. So that's why if you see the definition of norm, see that how it is written. This is just a notation with the 2 bar lines and over V. Let me write here, maybe it will clear to you. The norm word is, this is just a notation, you can make it as a function also. This is defined over V2R. What it mean that how it will be defined? Let's replace with the F it here. So it will be like V, a vector here V, it will give a real number. So let's say some alpha. So in this form, if you want to say this is, so this is, it will give a some real number. So this norm is actually induced from this length word. Actually, what I am doing, we have a vector and I am measuring its length. So not exactly it. We want to not only this length word in R2. We want to suppose your vector space is changed with the polynomial something. So how we will measure the length of this polynomial something? That's why the norm word came, and to measure the length. Actually, norm is mainly came for the measuring the length of a vector. So this is the more generalized form of a length. So
what is FB here, sir? FB?
FV. So FV, I'm just saying this is just a notation. This is just a notation of a function. You can change with this word. I'm saying this one. Okay, this is just a notation, changing f notation with this bar lines.
So
Okay,
FB is equal to alpha.
ab is equal to some real number.
Okay.
Means if you have what I mean to say, let's one by one, let's go. So suppose you have a vector space. Okay, if you have vector space over R, so I defined a function on this vector space. Let's say I defined a function on this vector space. The domain is the vector space, codomain is core real number. Okay, if this function satisfies some condition, the first condition, what is the first condition? Norm of v should always greater or equal to 0, and if norm of v equal to 0 implies v equal to 0. Sorry, this means f. Let's remove this with the f. I made a mistake. This is f. This is f here. This is f. V is equal to 0 implies v equal to 0. The second condition is f of u is a vector. V is a vector from this phi. U and v taken from this v. This is less than or equal to fu plus fv. So this is called positivity. This is called triangle inequality. The term. Third term is f of c times c is any scalar multiplied with the vector. It will be mod of c f of b. If this function satisfies these three conditions, as here, let me finish. Okay, this one. If it satisfies these three conditions, then we will say this function is a norm on phi. This function f is a norm on the vector space phi. As here, the same as in the inner product. For the inner product, we have some function and we have four condition. If that function satisfied four condition, then done. That function is called inner product. Same here, we have some function, but that function, inner product function, was or is v cross v over r, but norm function is only on phi.
I have a question here.
Huh?
When we are saying f of v is equal to 0 only when v is equal to 0, isn't that normally implied? Is there any other condition under which v is non-zero but f of v is 0?
It can be, but that function you will never call as a norm. Yeah, there are some functions which, yeah, okay, v cannot be 0 or f is equal to 0. I will tell you that some function I will give, but yeah, that function you will never call it. This function is a norm on phi. Okay, that is a simple function. Now this is a simple function.
No, I'm referring to from the perspective of the length of a vector. When you say length of a vector, yeah, when we're talking about length of a vector, unless it has some magnitude, I mean, right now we are talking norm is a crude approximation to the magnitude of the vector, correct?
Yes, correct.
If the vector is having 0 length, then it is automatically 0. So I'm just trying to see, imagine a scenario where a vector is a length, but the magnitude is 0. Is that a possibility?
No. So that's the game. That's why if it is 0 and the length will like, no, sorry. The thing is, if this is 0 and this vector is not equal to 0 for the length word, it will ever true for the length word. No, never it will true. No, for the length word.
Correct. That's the reason why I'm asking, is this really necessary? Are there non-zero vectors whose length is going to be 0 is what I'm actually
so the length is never 0 for the length word. For the norm word, it will also, because norm is induced from the length word. Norm word is, you can say, first length word came, then norm word came.
Correct.
So whatever the property for the length is satisfying, that's why it's needed. It should also, because this is some norm word is some extension from this, so it should also satisfy as the length word satisfies. So once you have length is 0, that vector should be 0 for the length word. So for the norm case also it should be like that.
Okay.
That's why. So once you have like this, means once that function satisfying these three conditions, then you can call that function as a norm. If any one of them is not satisfied, that function is not satisfied by that function, then that function will be a function, no issue. But that function you will never call as a norm.
Okay.
So we will see that, okay, somebody, but yeah, we will see some function which have, okay, like this, maybe satisfy these three conditions, but missing with this term. Still, you will say that function is not a norm.
Okay. Okay.
So let's see with the example. So in this video, only norm. And now the sir is now telling how the length is come as a norm word. So that's why. Okay, now sir is solving some example here. One concept is remain. So I will discuss that also. That's all in this video. So let's see with an example. Okay. Okay, so see that we have with the bunch of options. So I am taking this fifth question. It have bunch of options. So what is in that? It is not written properly. The notation form, it just worded the word like norm. Which one of the is norm? So what is the first option says? Okay, so what I'm here? We are taking R3, and now I don't think there is a problem with this F if I replace with this notation. Two vertical lines, means two bars here. This is here V plus W. This F, this lines with just change F, or this F is changed with this vertical lines. So this is C time. This is just a notation. Only we are just notating it like this function. Suppose we have a vector space this, and the function from V to R3, sorry, R. This function defined like norm of, okay, defined like, okay, a vector. This V is from R3 means it will be like coordinate wide X, Y, Z. If you are taking V, let's say V is equal to V1, V2, V3. It will be, it have three coordinates. So it is defined like, or if you want to write in more precise way, this is V1, V2, V3. It is defined like, let's take an example, this max word, max. Okay, so max written as A1, B1, C1. A is our vector, A1, B1, C1. So it will be like max of V1, V2, V3. So this is the function. The question is this function is a norm on vector space R3 or not? So is it clear how the function is defined? What is this one? Anyone can unmute yourself and tell how it is, how it look like. No. So let's take a vector. I am taking a vector. Let's take V is equal to 1, 2, 3. This is the vector from R3. So norm of V, no, norm of not norm, this function, we will not call it as a norm. This function, this V is defined like 1, 2, 3. This function is defined like max of, as here, V1, V2, V3. So what is max in this 1, 2, 3? 3 is here. So see that how the function is. This is function from the vector from real line. This is a vector, you got a real number 3. So is it clear how this function is defined? Am I audible?
Yes, sir.
Or I am is
Yes,
it clear
sir.
to all of you, or it is a very different thing? If not clear, please stop me. I will repeat and repeat again. Okay, so this is now as the function we want. This is a function we want to check it, is this function is a norm or not. What it means that we have to check all these 3 conditions. So let's check here. So we have a vector. I'm taking from a vector from R3. Let's say V equal to V1, V2, V3. The first condition is says norm of V means positivity, and if this equal to 0 implies V equal to 0. Okay, so let's take this right hand side. This is norm of V equal to not norm. This function is function V equal to this V1, V2, V3. Okay, this is equal to max of V1, V2, V3. So is this ever greater or equal to 0? Always it will be greater or equal to 0?
Not a must.
Not necessary. If you assume V equal to -1, -2, -3, right? So then this, what will be this? Max of -1, -2, -3. What will be max here? -1, which is less than 0.
So, sir, will this be norm? So this will not be.
So
norm.
this is not a norm.
Yeah.
It should be greater than 0, but this is less than.
Since it's failed the first condition, do we need to check the
No,
others?
no need to change the next one. That's why I am going to change with the function with the next option. Let's check this. This will tell more precise something more. This max of bar means absolute value of the coordinates. So again, I have function. We have a vector space. I have a function like this. Or let's erase with the word with the norm, this vertical y with the this f word, it will be more clear. We have a function like this, okay, from R, okay, and it is defined f of v equal to, our v is v1, v2, v3 equal to max of mod of v1, mod of v2, mod of v3. Okay, so we have this. Is this function is a norm on a vector space V? V means over here R3. Okay, this V is R3. So we want to check is this function is a norm or not. So how do we check again? So say first let's check the first condition, which says f of V should greater or equal to 0, and this should also happen if f of V equal to 0, if and only if V equal to 0. So let's take here f of V equal to max of V1, V2, V3, all are absolute values here. Okay. So you know that for the any case, this is a positive, this is a positive, yes, this sir. Is a positive. So for any case, it will be always positive, no? This max of positive values.
Yeah.
It will means it says always it will be greater than 0. Because you are taking the maximum value from the all positive value. Whatever you will give, minus you will give here, the absolute value of -1, it will be 1. Similarly for others. So always you have to choose from the positive values. So it means it will have always greater than 0. So that means, okay, first condition is somewhat satisfied, still remain to this one. F of V equal to 0, V equal to 0.
Yeah. And it will
So
only
let's
be
assume that.
possible when all will be 0.
So let's assume that this is equal to 0. This implies max of V1 absolute value of V2, max of absolute value of V3 equal to 0. Now again, whatever the max here, all are positive. When it will be 0?
When V1, V2, and V3 will be 0.
When, see, max we are taking, no? So it means what? It means what? Maximum of 0 means if someone is 1, it will become 1.
Yeah,
It means all should be 0. Then it will possible.
Yes.
That means says V1 is equal to 0, V2 is equal to 0, V3 is equal to 0. So our V is our what? V1, V2, V3. Means 0, 0, 0.
Yes.
So what we assumed this is okay, true, but we reached okay, V equal to 0. Similarly, you can go back also. You can easily check. If V is equal to 0, then max of 0, 0, 0 will be 0. That means f of V is equal to 0. What it says if and only condition satisfied here.
Yes,
That means first condition is satisfied.
Satisfied.
Now let's check for the second condition. The second condition is for the triangle. That is called triangle inequality. When you come, there is another something name is the norm word with changed name with the something name. This is something name is there. This is wider than the norm. Something in when you come in math in when you study about the functional analysis, is that. So like length, norm is the extended form of length, but some other word is come for the norm, extended form of the norm. So okay, no matter. Let's do the second. Is here? This is called the triangle inequality. V plus U. Oh, sorry. What I'm saying? F of V plus U. This should satisfy. Okay. So let's say V is equal to again our V1, V2, V3. And let's assume U equal to U1, U2, U3. So F of V plus U equal to F of
Sir,
V1.
V is max of V1, V2, V3.
Max of V1, V2, V3.
Okay.
This is plus U1, U2, U3. Max of not absolute of max, means max of absolute values.
Absolute. Yeah, yes.
Okay, so you have this one. Now add it. Take the left hand side. Now after this, you need to add these two vectors. Once you add, it will be V1 plus U1, V2 plus U2, V3 plus U3. Now this is a single vector. Now
Yes,
the
sir.
definition of F is max of mod of this first one, V1 plus U1, max of V2 plus U2, max of V3 plus U3. Okay. So this you have. Now is this we want to, this is the left hand side. Now take the right hand side. Right hand side is F of V plus F of U. So max of F of V is our V1, V2, V3 plus max of mod of U.
Sir, why you are adding this, sir?
No, this is the right side. No, I'm taking the right side of it.
Yeah, you are taking right side, but f of V is max of V1, V2, V3. Why you are adding this?
No, I am not adding here. This is the separating max of this thing. This is the first definition here. for the first u. Now the second you needed no max of u1, u2, and u3.
Yeah, sir. But why is this addition sign between V1 and V2? V2 and V3. There should be
Sorry.
comma. There should,
Sorry.
yeah.
Here is comma. Sorry. Here
Yeah.
is comma. Oh, here is comma. Oh, sorry. Here is comma. This is now plus here. So this we have f of u plus v. This should satisfy f of u plus f of v or whatever vu. This inequality should hold.
Yeah. Yes.
So you know that there is a property that if you have two real number a, b, this is satisfied, right, for any real number, for any real number, for absolute value of a and b belongs to real number. What I mean to say, if you have 1 plus 2 absolute value of 1, 2, this is less than absolute value of 1, absolute value of 2. It is the general case for the absolute function. It is always true. See that it is 3 here and right side is also 3. So less than or equal to. If you assume a equal to -1, okay, and
Plus
b
2.
equal to 2. So left side you will get here 1.
Yes.
But if you expand according to this one, you'll get mod of -1 plus mod of 2. So mod of -1 is 3. Sorry, this is less than or equal to will come because this mod value is 1 plus 2, which is 3 here. So actually satisfied. 1 is less than 3. So this is the general case for mod function. Mod function means mod value of this should always satisfy. This used to satisfy. So same case is here. So let's take this one to here. So means max of. So this actually equal to now will shift it to as the less than because of this when we will expand here. So this is mod of v1 plus mod of u1 plus mod of v2. Here not plus here is comma. This is, and now this one is expanded to v3 mod of this one. Okay, till now is it clear? No, this mod is just expanded like this. Am I audible?
Yes, sir. You are audible.
Okay. Yeah, maybe it is somewhat some more specific function like mod function, max function.
But sir, do we need to separate it in this one first? Because if we take the max of this, the max value will come out. It is of left hand side, and for right hand side, the max value. Suppose V1 and U1 are max. Then we are getting from left hand side max is V1 plus U1 mod, and from right hand side mod of V1 plus mod of U1. So do we need to do this one?
No, actually, so that is a specific case. Now we are trying to prove in this general case. Okay. We are trying to, yeah, okay, that is no issue. If you are, you know that okay, v2 is greater than this from all. So assuming to be v2 is here greater than this two, so it will give v2. Okay, mod of v2. And suppose someone is u1 is greater than, then it will give mod of u1. You got this one. Okay.
Yes.
Okay. So from this equation, but from this one, which one will be greater than? So once because of this mod property, this always holds. This always holds here. That's why okay, we know this one. Okay, but we want to make it separate because this is also hold. So max of something is we can make it more because this is now somewhat greater than to this one.
Yeah.
This number is greater than this one. This number is greater than this one.
But if minus is present, then this will not hold.
No, it works, na? It will. Yeah, because of this property as the mod function is there. As we just
For
check
positive,
now,
that
minus were there, still we can do. That's why this number, this mod of the addition with 2 is lesser than mod of when we separated it here. So
Yes, sir.
this number is greater than this number. When we separated here, this number is greater than this number. When we separated here, this number is greater than this one. So we want to make it max. We want to take max of it, greater numbers. So still then inequality will come, na? This is greater than with this one.
Yeah.
Now max, when you have this greater than this one, now you can, what is that? If you have two numbers, so max property is another property that it will hold when you added two numbers here, okay, two positive numbers, and when you added, and if you want to add with the separate thing, okay, still this term's going to be greater than this one. The reason is the max. If you say in the real life, I mean say on real line, okay, max of 1 plus 5, 2 plus 3, 1 plus 2. Okay. Now let's max of 1, 2, 1 plus max of 5, 3, 2. This is the same case, na? Taking as the first one here. This is the very similar case with this one. We added here, and these are the separate things. Max of this one will be 2. Max of this one is 5. It gives 7. Okay. Now let's add it. This will give max of 6, 5, and this is 3. This gives 6. Still you can see that separated one is greater than this 6 one. That's why I mean to say, if you take the separated one, it will still greater than this one. What I mean to say, this is greater, this number. This term is going to greater than with this number. Okay, it will take time. This is the max function. This is one kind of max function. You didn't go through, but still it will not teach somewhere it will come, and you have to, what is needed at, you have to search yourself on Google or somewhere, go to there and see the max, how the max function is behaving. So no matter, I just given the idea here, what's happening, what is the use of max, or what is happening here. So actually this triangle inequality hold for this max function. That's why if you see that this option is going to be correct. Actually this max function is a norm. Is it not clear?
Yeah,
please let me know. If not clear, I will give with the example. Maybe I will write in more precise way. So what is happening, what we want to prove, let me repeat again. So we want to prove this one. Okay, so we assumed two vectors and added them as according to we took the left hand side. Okay, one by one we are going to here to here. We reached here. Okay, this is the left hand side. This is the left hand side. Now let's take the right hand side. We have right hand side, this one. Okay, as the property of right hand side, we are going this one as we saying this is comma max of the coordinates, absolute value of the coordinate, max of the absolute value of the second vector. Okay. Now what is that? There is a relation. There is actually a relation with this one, mod function, and with this whole. This is called again the triangle inequality of absolute value or mod function. So actually what is happening, if you add two numbers, and if you take the absolute value of it, and if you take the absolute value of separated one and then add, then it will be always greater than with this one. So same thing is happening here. Let's jump to this one. I just make it here. What is the property here happening? This number, because of this property, this number is going to greater than this number. This number is going to greater than this number because of this property. That's why when you take max of it, the greater number, the whole number greater than this whole number, because you are taking the max of the greater numbers. As here we are taking, these are the greater numbers in compared to these numbers. Okay, now another property of max is here. When you are taking this greater number with the separate here, as here what we did here, we are added here, okay, separated. We added these two numbers, like we have these numbers. Okay, in adding form we are making the max, and in separated form, this is 1, this is 2 here, this is 1 here, this is 5 here, this second 3 here, this is 2 here. And we are making the max of in adding form and separated form. And what we see that this, after adding whatever we are number getting 6, and after taking the max of separated thing and then added, we got 7. And this 7 separated one is greater than this before adding. Means after adding. So what is happening here? The same thing. This is going to be max of V1, comma, max of V2, max of V3, plus max of U1, max of U2, max of U3. This is this number separated one is greater than after the means whatever the added we have, because you can compare with the, actually this can be proved, this can be proved in the mocks, in the mathematically. I just took in the example form. That's why now what we reached here, f of u plus phi means here this one is greater than this one. That means this holds, this inequality holds. So what it means that this max function of the absolute values of coordinates is satisfies the third condition of the norm.
So, sir, basically we are just seeing that both the absolute function and the max function would give greater values for the individual values. I mean, the max of individual values rather than their sum, both in the max function as well as the absolute function.
It will helps to make in the that triangle inequality. Means it will helps to satisfy the triangle inequality. Yeah. So don't worry, it will not, like, it is an activity question. It is in, you can see that in the level 2. I think this is not, there is level. Yeah, it is in level 2. So just to give an example, it will not really, it will be like in, it will come in the tweet kind.
So this inequality has a name because I think in activity 7.3 there was some name to the inequality.
Yeah, triangle inequality. This is called triangle.
This is called triangle inequality.
Yes. Yeah. So now the remain third one. Third one is very easily can be checked. You can, where is the third? Third one is, my page is finished here. Let me write here. Third one is, okay. Third condition is f of CV equal to mod of C f of V. This should satisfy. So our V is V1, V2, V3. So f of CV equal to f of CV1, CV2, CV3. This will come. And this is equal to max of absolute value of CV1, comma, max of CV2, absolute value of CV2, absolute value of CV3. So again, you can see that it will be work as a max you can make it absolute. Here each time multiply with C, mod C, you know that if A and B is here, it is exactly equal to mod of A, mod of B, this property. Absolute value of two number multiply with the each other, it will be make it separate. What you mean to say? 2 into 3 equal to absolute value of 2, absolute value of 3. Absolute value of 2 minus 3 equal to absolute value of minus 6, which is 6. Let's make it separate. This is equal to actually mod absolute value of 3, absolute value of minus 2, absolute value of 3. So absolute of minus 2 is 2, absolute value of 3 is 3, which is 6. So actually this is the general case. It's happened with the absolute value of the numbers, real numbers. So here similarly you can make it mod C out, and max of it will be implies as a max of mod of V1, mod of V2, mod of V3, which is exactly equal to this one, mod of C times this is the our f of V. So third inequality also holds. Third condition also holds. So this max function, whatever the absolute value of the coordinates, satisfied actually this norm. So this function is actually a norm on the vector space over R3. So don't worry, but I hope what I mean to say, okay, this is a like max and absolute max made a mix, very like a more pure mathematical thing. But what I mean to convince you, what is a norm? That's the motto I want to tell. If you have a function, if satisfy these three conditions, you can call the function as a norm. That's what I want to say. Don't worry with this absolute thing or max thing. If somebody is asked, it will surely give a not a tougher thing, simple one. It is not going to be a very dangerous.
Yes. So inner product and norm is a function.
So there is a relation. So that's why that's the remain thing. So is it clear how we will say when we call a function as a norm, when we call a inner product as a norm? So we need to each time check.
If the function satisfies all the four properties of inner product, then it will be called as inner product. And if it satisfies the property of norm, then it will be called as norm.
No.
That's
it. But be careful with that. Our inner product is defined like V cross V over
V
R.
cross V,
But norm is our defined on over V, not here, there is no cross over V2. So domain of the function is the different of these two functions. Yes. Domain of the function is here V cross V, but here V only. Yeah, range of both function is same. Range in codomain. So till these things are called the norm and inner product. There is one more concept is remain. That is a simple one. Let me write to here now. My page is filled. So the concept is, once you have a vector space, okay. If you have a vector space over R, and you have an inner product on this vector space. Suppose somebody gave you an inner product. Let's say I'm saying, for example, I'm saying our V is R2 and our inner product is dot product. Okay. Once you have this one, so this vector space, now you can call it as a not vector space, you can call as the inner product space. What I'm saying, if you have a vector space and okay, I defined an inner product on this vector space. Okay. So we can call this vector space as an inner product space also. Previous one, this is just as a vector space. There was no norm. If we remove this inner product word, so simple, this is a vector space. But if there is, I defined an inner product on this vector space, then this vector space you can call as a inner product space also. Okay. So once you have an inner product space, what do you mean by, if you have a vector space P, okay, and if you have, there is an inner product on this phi, so there is a relation in inner product and norm. What is the relation? Actually, this norm, let's take a vector from this vector space V. Okay. So, okay. So I can, our norm is defined like from where? This is from V to R. Our inner product is defined how? V cross V to R. Okay. So let's define a norm on this inner product space V. How we are defining norm of V equal to root over inner product with the same vector. Take the inner product with the same vector. Then take as a, this, take the, call it as a norm. So actually this norm, how it is defined, this is actually, this function is a norm on inner product. Okay, maybe it is a more theoretical. Let me take an example. I am taking vector space as R2. Okay. And inner product I am defining as a dot product on this vector space. So what will be, I am taking a vector, let's say 1, 2 from R2. Okay. Then what will be the norm here? With this definition means norm of 1, 2 equal to, take the root of, I am missing something. I am making, here is will be the absolute value. No? What is that? Something is.
Sir, actually under root contains value greater than equal to 0.
So there is a, after taking absolute value, then norm is defined. No? Something is there. What is that?
No, sir. Not. No absolute
what
value.
is that? Okay, how it is defined? Norm of V is equal to. Sorry. There is absolute value means, okay, that is a positive. Oh, mine is also correct. No issue. Why am I saying? See, you know that for an inner product, for just now I told you V cross V always greater than 0. So no need to take absolute. So just it will work. For myself, I want to skip from the negative. I forgot about that. Okay, it is always a positive. That's why I put mod here. But no need of that.
V comma V. Sir, V comma V is the same vector. V dot V.
Take the inner product with the same. So what is I'm writing here? Let me write here. 1, 2, 1, 2. This is the definition in the more precise way. In the example form I'm saying. So this is the norm of this vector. Okay, this norm is called, this norm is actually called induced from inner product. This norm is called norm induced from inner. No need to remember this word. Actually, this norm is actually induced from this inner product. This is okay. This is okay. Root over is there. So whatever I told you here theory, the same thing is here. The differences is I took a vector space as here. Norm is only on phi. So same thing is here. Norm is only on a vector 1, 2. Okay, inner product is need to take the with 2 vector. So take the inner product with the same vector and take the root of it. So this is called, this is the relation between norm and inner product. This is the, you can see if you in video, if you watch now the video, it will be more clear to you how the sir is doing and what concept he is teaching. And actually here sir is proving how this whatever I defined here, how this function, actually this is a function is still remain to prove. Actually this is a function, we need to prove this is a norm. So we need to prove all these three, we need to this function should satisfy all these three conditions. So actually, sir is proving all these three conditions is satisfied here. So if you watch clear, again, it may be more clear to you. Is it clear what I'm saying?
Yeah, yes, sir.
Okay. I'm looking only 17 participants. Okay, that this is all about for this week. What is inner, what is norm?
Sir, could you look at question 3 of AQ 7?
Which one? AQ?
7.4 question 3.
7.4 question number 3. So okay, let's it's remain to see it. So this one, choose the set of correct option. So the two vectors satisfying the triangle inequality, two vectors do not satisfy triangle inequality. So there is no theory, just you need to substitute here.
Sir, what is the third option? We've not heard of it. So it's just what is given?
So actually this is given equality named Cauchy-Schwarz inequality. So,
but it is defined by this particular function.
It's called Cauchy-Schwarz inequality.
Only this inequality is present. Sir.
Otherwise, we need to put this in this.
Sir, how would we assume that this inner product AB would be just a dot product?
So yeah, in this question.
Do we just assume or we just take because dot product to
here is the Riemann. Okay, it is given R3, but it should be written inner product as a dot product and norm as a induced inner product. 7.4 it is, na? Okay. So
how do we know
so actually one thing I let me tell you, actually this question is assumed generally. Suppose if you are working with R2, R3 in Rn anything, okay, if you are working with Rn and suppose in some question maybe it forgot to give you the inner product, always assume inner products are dot product. Means dot product is there, means inner product as a dot product.
And norm as?
Norm is induced from the dot product. Whatever I am teaching.
The formula for length of a vector.
This one. No, this one. Actually, this says the length itself. But
yes,
once you have inner product, you can do with the norm as induced from this one. So once you have inner product, you can do the norm as the induced from this dot inner product.
Whatever. In the equation that you just showed, where the norm is equal to square root of inner product, do we compute the inner product and then take the square root, or whatever is the vector that is there?
So what is needed to here? For the left side, you need to take the inner product and take the absolute value. Okay. Right side is you need to form the norm of it. So first find the inner product of AA and then norm how it is root of that. Similarly for B, take the inner product BB and then norm is root of it as here. Means if you want to write in more precise way, it is like this. So it is here written like this. So it means take the norm of a root over into root over norm of inner product BB. This is the mean.
My question is a little more than this. Okay, once you write AA, do I compute the distance AA as in what do I do with it? When you have, in this case, A is written as
AA means what? Now you need to compute AA, na? AA is what? A dot product is there. This is inner product as a dot product.
Okay. Okay, that's what
So
that was my
that's
question.
I meant to say. If there is no inner product written for the Rn case I am saying for any R2, R3, any, if an inner product is not mentioned, you can always assume inner product as a dot product.
Okay.
This is explicit. Many times it's explicit. If inner product is not given and notation is used like this, or also norms is also. So norms you can think this form. Norms is in this form. The inner product is the dot product. Okay.
Okay.
Is
Okay.
it clear?
Yeah.
What is needed to do in this third option? Is it clear?
Yeah, dot product of A and A is going to be 0.4 into 0.4, 1.3 into 1.3, and minus 2.
So actually what is happening, actually let me tell you the more thing is, this dot product is actually the length of it. Length of the vector.
Yeah.
Here,
Yeah.
if you
Yeah.
simplify it as a dot product, so actually it will give the length of the vector. Similarly here, so you can work on the as a length of the vector. In place of just writing the inner product, you can take the length of it. It will also work when the inner product is not given in the question. So dot product, when you assume as a dot product, it work as a length of that also. Okay.
Thank you.
So, and now the same questions are writing to be like to check which one is as inner product. So that's all for this session. Do you want to ask anything?
Hello, sir.
Yes, can
I have
we
a
ask
doubt.
a few activity questions?
Okay. So yeah, let's quickly deal with the activity.
There's this AQ 7.1,
7.1.
question 5. If you could look at option 3.
Okay. Question 5. Option 3. Yeah, this one.
Yeah, this I could not prove.
So the option is, if A and B are similar matrices, have, and the system is given AX plus B has a unique solution. So then this system BX is equal to B also has a unique solution. Is this option is true or not? So how you are solving this?
All I know is B will be inverse of P. A
like this, huh?
P, yeah.
Okay. Now, so now what you are doing?
I did not move from there. I tried. I tried to write this.
Okay,
Sir, can I tell?
So what
can
is
I tell how I solved it?
Yeah, sure.
Sir, it's given A and B are similar matrices, and AX is equal to B as a unique solution. Okay.
Yeah.
So A and B are similar. So determinant of A is equal to determinant of B.
Yes.
And if AX is equal to B has a unique solution, that means determinant of A is not equal to 0.
Yes, that's the infer.
Yeah. So determinant of B is also not equal to 0. Then we can infer from there that it has also has a unique solution.
We have this system and determinant of B not equal to 0. It says
that's a wonderful solution.
Yeah.
That's the infer.
Yeah. And I think even question 6 also is a little tough in this, especially 1, 2, and 5.
So which option, or maybe all option?
I know. I understood the fourth option. I think the first one I could not understand how it could do.
Okay. So if we have A and B non-zero, what it means that? It means means A and B are invertible, right?
One of them is at least invertible. One of them is non-zero.
It is given that if determinant of A or determinant of B, okay, one of them sure is okay, no issue. So let's assume determinant of B not equal to 0.
Yes.
That means B is invertible, means B inverse exists.
Yes.
and I want to say is that AB and BA are similar or not? That's the question. Similar or not?
Yeah.
So what we can do means I want to say these are similar or not. It means BA equal to P inverse. Assume that okay. Let's do that. Okay, assume okay. This is similar, or maybe we will reach a contradiction or not. Let's see that. Okay, if saying this option is similar, let's write that. Okay, this should happen. This should happen.
Yes.
Okay. What it means that this is P inverse is P should exist. There exists P such that this should happen.
Yes.
So we need to find actually P if these two are similar. So there is one thing like actually we know that A equal to as A we can write, or A equal to A we can do, or maybe not like this, or maybe AP equal to, we can multiply AP equal to here, or maybe like this, B equal to AB equal to BA we want something. AB means BAB, and if we multiply B inverse both side, because B is invertible, so B inverse. These two are the same. So if you multiply B inverse both sides, it will be B inverse B inverse. So how it will be? This is AB here, and this is going to be
B inverse equals to I unit matrix.
yeah, actually there is a relation. Using that you can do. I'm missing something. Okay.
I think you have arrived at it. I think the second right hand side would be BA into the identity matrix.
BA something. It will be BA.
Which will be A. Yeah, and this over here, then B would be our
okay,
P.
it is correct. Okay, now it's fine. Na? Okay, this AB and B inverse.
Yeah, so this would be our P, right?
This yeah, this B is our P is our B, or whatever you want to say. This is AB here. This is BA, and B our work as a P or P inverse, whatever.
Yeah. So B would be our P and P inverse. Okay.
That's why it's going to be the same.
But this would only happen if B was invertible.
If you assume that's why assuming any
So
one of
determinant
them
is non-zero. Yeah. Thank you, sir.
Can you elaborate on the last bit, please? B into B inverse, I understand it as identity matrix, but what's happening on the left side?
Left side is the same thing. Whatever. Okay, this is going to be identity. So we got BA, but it is as it is. So we can say this side is our motto. Like
Correct.
we want to write side AB, or maybe BA equal to P inverse AB P. This is we want. For to saying the similarity. So we have inside this one, and our P work as here you can see inverse kind of thing.
Okay, but how was it actually helping me prove that AB is equal to BA?
So actually we got we got P as a B or B inverse, whatever you want to write is. We got actually what is the definition for similarity? There exists a P such that A equal to P inverse BP. So this would happen for AB for to make a BA are similar. So we got actually P as a B inverse or B something,
no,
whatever.
we got P as a B.
B inverse, yeah, or maybe actually how the definition is P inverse is. So you can write B as a B inverse AB B inverse. is equal to BA. What I mean to say, BA equal to B inverse of inverse AB B inverse. So our P's work has here B inverse.
Okay.
No, it is
Okay.
it is like a P inverse AB and P. So there exists actually P such that this is happening. That's why these two are going to be similar.
Okay, but how are we actually establishing that it is invertible? Or how is invertibility?
So it is given that determinant of assuming any one of them is non-zero.
Yeah, if A or B is not zero.
Rajat, could I ask my doubt?
Sure,
Could you
sure.
open week 6?
Sure. Just 1 minute. Let's finish this. Okay. So is it clear?
Okay, sir. Okay.
Not really. I mean, like determinant part is not really clear. Okay, this part I understood. P is equal to B inverse. But how is that
So
determinant not being zero?
Determinant says determinant is non-zero means our matrix is invertible.
Correct.
So once our matrix is invertible means we have B inverse. Means if we have B, then B
possible,
inverse
you mean to
exists.
say. Okay.
So once we have V inverse, so we are able to get a relation with such kind.
Okay.
So our P work as a B inverse.
Okay.
And this is true because B is invertible. So P is exist here.
Okay.
Sir, but it's not must that if the two matrices have the same order and they have the same determinant, then they're similar. That's not a compulsory, right?
So actually when similar, then determinant is same, rank is same, trace is also same.
Order is same. But then but just having order and determinant meeting those two conditions does not make it similar.
No, not necessary. Means order means when you are comparing two matrices, the order will be always same. Assuming to be order are same, then we are able to compare.
Yeah.
And if you want to compare A is similar to B, means order is both matrices have same order.
Yeah.
We meant to check these P's exist or not. If order is not same, then equivalent term, equivalency word come na. Equivalency, what is equivalence? Two matrices are equivalent.
Yes.
For that, if order is not same, then equivalence term came. For similarity, order are same. Clear?
Sir.
Now you can ask your from week 6.
Sir, I had just one more question from week 7.
Just one minute, let's finish this week 6 also. He had asked in starting itself. Which one?
Okay.
Which activity?
6.1. I have 6.1, 6.2, 6.3, and solve with us also.
6.1.
6.1, question 4.
Okay, question number 4.
Yes, question number 4. So in question number 4, how to get the solution, or how to I got that is a onto not but not 1 1, but in the solution there is a given that is a neither on 1 1 nor onto. So how's it?
Okay, you got P, na?
Yes, I got P. I put the value. There is given there are given point. So I put this point, which solution satisfy
okay,
those
so
points.
you using that you got T is
yes.
some. Okay, so which one is T here?
T is C and D.
C and D. Okay, C and D.
Yes.
Okay, this is multi-selected. Okay. C and D. Okay, let's 4.
Yes.
Okay, C and D. Okay. So now need to check 1 1 onto.
Yes. Here I saw that there is there is a 2 independent variable. That is means nullity is 2. So
okay,
so that is not a 1 1.
Correct.
Oh, yes. Okay, so that is not a onto.
For onto still remain to check.
Yes, for onto rank must be same. Rank must be same dimension of code event.
So
yes.
actually one thing you can do if you want to check onto. So you are
Yes.
able to get nullity of the linear transformation. Na?
Yes.
Use rank nullity theorem to conclude the rank of the linear transformation.
So, could you scroll down?
Okay.
Little.
Okay.
Okay. That is there is a right hand C is a isomorphism. That is mean that is a 1 and on 2. So we are already concluded that is a nullity is 1. So that is not a 1-to-1.
Okay.
How that is possible?
Okay, just one minute. Okay, let T be linear transformation device. Answer. Which of the following is appropriate definition for T? Okay, so these two are same because of we will get a unique T. You can say this one. Okay.
Yes.
Now what is the option is there? T is going to be an isomorphism. Okay. Okay, T is going to be an isomorphism. So how you are? So you proved that this is 1-1 or this is not 1-1.
Yes, this is not a 1-1 because nullity is 2.
Nullity is 2. So,
yes.
But how you are concluding this this linear transform has nullity 2?
There are 2 independent variable
Here for this one.
Yes.
Okay.
Yes.
Independent
Yes.
variable. No, for this
And
there would be one independent variable. No? For this you will get a one independent.
When you take question 7.
Sorry.
Option C, that is z y comma z.
Okay.
When you are equals to 0, 0, that is y equals to 0, z equals to 0. That is means 2 independent variables.
Okay, if you assume I'm solving it. T of x y z equal to yz. We have this one. Huh?
Yes. Yes.
Okay, so if you assume it is 0, 0, it says y equal to 0 and z equal to 0.
Yes.
So T of just one minute. T of something like 0, 1, like 1, 0, 0 also gives this one 0, 0, 0.
0. Yes.
But actually you will see that there is a condition have this one. Whatever you will vector take here, this should satisfy here. So what it means that if you have y is equal to 0, z is equal to 0 implies x is equal to 0.
Yes.
That's why it is going to be 1, 1 only. Means you don't have any independent variable.
Okay.
All are dependent.
We need to check first conditions.
Because of this one, like you got y is equal to 0, z is equal to 0, but the vectors whatever you will take, it will satisfy this equation. And when you want to check here y is equal to 0, z is equal to 0, this says x is equal to 0. So then it means the vector only 0, 0 have 0 image. This says this linear transformation is 1, 1.
Okay, sir. For onto, sir?
For onto, use rank nullity theorem. What is rank nullity theorem?
Okay.
If your rank is linear transformation 2 and dimension of the codomain is also 2, then your linear transformation is onto. This says this thing.
But that is gone R3 to R2.
R3 to R2.
So rank.
But not R3 to R2, W to R2. Not exactly R3. W to R2. And W have dimension 2. See that?
Yes.
W have dimension 2. That's why it's happening. That's why it's going to be isomorphism. It is actually onto.
Okay. Slightly tricky.
So try it once. Try again. You can do that. Try one.
Okay. Question number 6.
Okay. So I will take the question number 6, but now I will take the question from week 7. Then I will take you from week 6.
Sir. Okay, sir. Don't worry, sir.
Yeah. So let's do with this. Who have on week 7, because this is on week 7.
Sir, may I ask?
Yeah, sure.
Activity question 7.2, question 1.
7.2, question 1. Fine. Okay. Question 1.
Yeah. I don't know how to prove this.
Okay. So just now I said you for R2 this is an affine, this is L is an affine subspace. Which of the
Yes.
following corresponding will be the corresponding subspace of that affine subspace?
Yes.
Okay, can you tell me if there is a subspace of R3? So a subspace have zero vector, right? For any
Yes.
subspace.
Yes.
So you can check that which one have zero vector. Which of the following set have zero vector? Is the first in the first option have zero vector?
No.
No. Okay. For the second, third, and fourth have zero vector.
Yes. Yes. Then how would I choose between them?
How I will choose on between them? Now, if you take anyone can tell will be also good.
Is it a second option?
So for the second option,
because it is passing through zero.
Passing through zero, yeah.
And it is parallel to the one that is in question, x plus 2y plus x plus y plus 2z is equal to 6.
6. Yeah, actually this is the only one, but I want to reason why this is happening.
Yeah.
So how do we infer from this L how you will exactly find the corresponding subspace? So you know that this is for the corresponding subspace, this should happen like L is equal to V plus U. And our L is x, y, z such that x plus y plus 2z is equal to 6.
Yes.
X plus y plus 2z. 2z is equal to 6. So this we want. So how do we remove this u from this L? What will be u here? Sorry, this v. Sorry, this v. How we will remove this v? What
Maybe by taking 0, 0.
If you take 0, 0, no.
Because we can take any v, right?
Any v, but satisfying this L, no? This L.
Oh yeah, that x plus y plus 2z is equal to 6.
Take a vector satisfying this L.
Yeah.
What will be that? Can you tell me any vector? It will be.
Yeah, you can take 0, 0, 3.
0, 0, 3. Okay, 0, 0, 3. Okay, this is satisfying. So assuming to be this one, okay, this is, let's take now remove this 0, 0, 3 plus u. So if you want to remove this, so what will be exact u here? Your L is, you can assume u equal to, or maybe our L is this one. U is from something will come here. I want to find u exactly. Okay, so
yes.
See one thing. See, it is a simple way to saying just substitute here 0 for any. If suppose someone is giving here, so your u is exactly this one, x, y, z. I will tell the reason why. Not only saying to be just substitute 0 plus 2z is equal to 0. So this is your u, but the question is why. So how we will find this? So suppose for this question, for any question I'm saying, suppose such kind of relation is given, you can substitute here 0. That is your u. The reason is in geometric form. If I will tell you, this represent a plane. This represent a plane. Suppose this is the plane, because it is not passing through origin, because there is here is, and you know that in affine subspace, affine subspaces are shift of the plane passing through origin, means a shift of the subspaces. What it mean that it will be somewhere passing through origin, but our affine is shifted to somewhere.
Yes.
So what it mean? Shifted means it's parallelly shifted.
Yes.
If you want to find the parallel of this plane, how you will get? Just substituting 0, you will get exactly. This is the geometric approach, saying to be a geometric way. But
So even something like 2x plus 2y plus say 4z is equal to something would have also worked.
This will no. This will
If
not
it
work.
was
This is not.
no, there is no other option like that. But if it was something like 2x plus 2y plus 4z, would that have also been satisfying?
No. How it is? It is not going to parallel to this one, na? This one. It should be parallel to this one.
Yeah, I've just done a scalar multiple of it.
So parallel to this one means parallel to this plane means the coefficients should also exactly the same. Only the right side will be shifted.
Okay, right. Not just
Parallel means coefficients should exactly the same. Only the right side is the 0 and the shifted.
So that was the obvious choice then.
That is the that's why directly you can say. But in the geometric, in the algebraic, if you want to reach, so you have to assume that okay, x, y, z, this is the plane or this is the subspace satisfying yz plus cz is equal to 0 because it will pass through everything.
So actually, I did this through this, and I felt I had done a bit of a guesswork. And when I came then to question 2, then I was completely
so actually
clueless.
this is the algebraic way to do this. Okay. So this is x, y, and this is z plus 3. Ax plus by plus cz is equal to 0. So assuming to be this x, this is y, and this is z. And you can substitute here. Means adding to be this vector means you added to the vectors in the inside here. Means now if you assume this one, this one, this one. So this is a capital X is equal to X, capital Y is equal to Y, and capital Z is equal to say small z plus 3. Now substitute as you have the relation. Substitute here and you will get a relation in between them, and then compare. It will neglect exactly. It will give the some kind of this one. That is a longer process.
Yeah. Actually, this is not working in question 2. It's not working in question 2, the geometric one. Question 2, it becomes complex when there's squares.
This one.
How do you determine the affine subspace? Yeah, this one I didn't know.
So affine subspaces will be not a square kind of. It will be always a linear kind of. Degree will be linear always.
But I think one of them is correct. I think x squared plus y squared is equal to 0. One of them is correct. I also assumed it would be linear.
Y square is equal to 0 means what? X is equal to 0, y is equal to 0. It says x square plus y square is equal to 0. What it means? If you conclude the set form, if you suppose you have this one, x square plus y square is equal to 0, what it said? When it will be 0? When x is equal to 0, y is equal to 0. So actually your set is nothing but the 0 vector, that first option. It is just the molded form.
That's so if we have squares equal, then it's okay. Equal to 0, then it's okay. Some powers.
For equal to 0, it is okay because this represents a 0 vector only, nothing else.
But sir, in general, this topic is very tough. It's not very easy to understand.
May I ask something? When we're talking only about transformation of a, I mean, I thought it is applicable to any kind of a curve. Affine is only limited to lines, is it?
So actually, see, let me tell you a more explicit thing. In R2, in R3, let me tell you, in R2, your affine subspaces are lines only, or maybe 0, 0, or whole R2, or some points only.
How come a point?
These are the only affine subspaces. It will be not like a curve. Means x square plus y square is equal to 4. It says it is a curve, not a line.
Sure. It's a circle of radius 2.
Something. It is circle of radius 2 something.
So why would it be? I mean, like, sorry, maybe my question is to be seen differently. 1, 2 is a point on the plane.
1, 2 is a point on the plane. Correct.
So if it is a point on the plane, it's not
affine subspace. It is an affine subspace. Reason is why. So reason is 0, 0 is your subspace. Work as a subspace. So L is how define 0, the vector, let's say 1, 2, and with the 1, 2, and with the subspace, which is our 0, 6.
So any
Actually,
vector
1,
that
2
I
is
can add to something that is passing through origin is a affine subspace, is it?
Passing through origin is work as a subspace. But lines for the affine subspace, okay, lines are affine subspace, any points are affine subspace, or maybe 0 also work as affine subspace. 0, 0 means why it is a affine subspace. You can think as a L as a 0, 0 itself plus 0, 0, 0 vector plus 0, 0 that subspace as a subspace itself.
Okay. So when you say R3 is the plane that we're talking about always?
So for R3 have the all planes, whatever the planes you have possible planes. These are all subspaces. Sorry, affine subspaces. Also 0, 0, 0 in that. Points are in that. Lines in the plane are in that. All are affine subspaces.
So even lines are also affine subspaces.
Lines
R3?
are also in R3 are affine subspace in R3.
Okay.
The reason is simply take a line which pass through origin. Okay, pass through origin and make a shift off with this line.
Okay.
So this line is work as a subspace and shift off with work as a vector, and then it is shifted. So your affine is that line plus that vector, whatever the vector you are taking.
Okay.
That's the reason our lines, planes are as work as a affine.
So okay, then R3, R2 and R3 and R1 are the only possibilities for affine subspace, or even in R4 can we have affine subspace?
So in R4 you cannot visualize, so it will be
correct.
difficult. That's why your algebraic approach needed here. Otherwise, till R3 we can visualize, and that's why you're able to do with the planes and lines and points like that.
So algebraically, if you can prove it once again, please. I know you actually did it just now. Can you repeat that once, please?
So algebraically means point. If you in R4, if you will say, if R4 a point will be, let's say A, B, C, D, something point is there. Algebraically, yeah, it is visualizing how the point maybe, yeah, in R4, how it is, I don't know how we will write. So it will be like that vector itself, A, B, C, D with 0 subspace.
Okay.
So the points in R4 are actually affine subspaces. Similarly, if you are able to visualize planes, lines in R4, so actually those are the just shift of the planes which pass through origin in R4. I don't know, maybe not only plane in R4 now, a different scenario. Maybe it will be like it may be in R4 how it will be. Visualizing is difficult. Maybe structures are like that, may forms a subspace and then shift of that will work. So no matter. So that's why I needed to algebraic condition now.
So A, B, C, D plus 0, 0, 0, 0, when we actually add them up, I end up with the same thing. So that is when I say it's affine subspace, is it?
Affine subspace, yeah.
So, so all I need to do is algebraically add to the point in 3-dimension or 2-dimension 0, 0, 0, and if it comes out the same, anyway it comes out the same. Why do I need to actually check it as a affine subspace?
Yeah, you are obvious to see that, yeah, it's looking like a affine, but yeah, if you are asking that's why I am giving. Otherwise, yeah, it's work as a affine. If you want to, yeah, I just giving the definition. If visualization, or maybe you are asking the region, that's why I'm saying. Otherwise, okay, no issue.
No, what I mean to ask is, when we said R4, let's forget the visualization part. A, B, C, D. Okay, fine. If I add 0, 0, 0, 0 to A, B, C, D, it comes out as A, B, C, D. That happens in R4, 3, 2, even in 1. So why do I need to do this algebraic test? It's anyway going to be the same thing.
Yeah, okay, fine. This concept is not only for Rn. This concept is used for polynomial vector space. Then how you will visualize that? Polynomial will not. How you will visualize that? Then algebraic ways.
But polynomial, when we say we're going into higher powers, and higher powers anyway, we were just discussing that it is not affine space.
No. So polynomial means polynomial vector space, I'm saying. See, all functions form a vector space with the proper relation, with the proper addition. Proper addition means there is a operation, proper operation defined. So all functions, collection of all function or collection of all polynomials forms a vector space. Okay, with the some specific operation. This time I haven't remembered that operations. What are those operations? But forms a vector space. And now for those vector space, how you will visualize the affine subspace? For those we needed algebraic. No sir, algebraic way, because the polynomials. What there is nothing mean polynomials means a vector will be a polynomial in this vector space. So that's the nature of algebraic way. Otherwise, yeah, for this term only working with the R2, R3, R4, or maybe some matrices form. That's why it's okay. Otherwise, visualizing till week 3 is enough. I mean, enough means able to visualize.
Okay. And when we go to problem 3, it states x square plus y square plus z square is equal to 0. Okay, because it is 0. Okay, fine.
Again,
even
it is going to be 0.
It's a sphere, but it is of 0 diameter, so 0 radius.
Correct. Actually, this set is actually the 0 set.
Yeah.
But rest all are who have the degree more than 1. You cannot say this is in the video itself. Sir says these are not going to be the affine services. Only the planes, lines. This is also plane. Okay. This is the degree up to. This is not going to be a affine, because you can see that it's a multiple of 2 variables. This have degree 2. This is going to be a affine, as this is work as a plane. This is work as a plane. This is work as a plane.
Okay. The reason why I got curious is because when we start translating things, actually, if I do a normal translation of a circle, the curvature of the circle, like let's say the radius is 4, the radius is 0. From 0, I can actually make it bigger and then scale it up, and I get to 4 radius. That's the reason why I was a little confused as to why it isn't so. Okay. X square plus y square is equal to 16. Let me put it as that comes if I blow up the radius from 0 to 4. So when I'm translating, the entire line is moving, but here I'm scaling. Okay.
Okay, so let's move to the question. Maybe yeah. Anyone have doubt, or we can let's just end the session?
Yes, I have lots of doubt. Week 6.
Okay, on week 6. Or remaining, anyone have week 7 doubt? Okay, so I'm moving to the on week 6, and now then after we will end the session.
And week 7, if I have doubts, the next opportunity is only on Tuesday.
On Tuesday, yeah. Or you can post in discourse itself.
Okay, thanks.
Okay, 6.1 question number 6.
Okay, so 6.1 question number. Which question number? Question number 6.
Yes.
Okay. What is doubt here?
Yes. I can't solve this question. So how to solve this question?
So for that I will tell you. I will tell you this whole thing. This activity I have discussed in the last session, in my session itself. How to find the linear transformation and how we can contradict. Okay, this is going to be or not. Did you watch that? You were there, Rohit?
Okay. No, sir.
No, actually.
No, I am not there.
Actually, this is totally discussed. This one question I have remember. I had discussed this one. So, where is that?
Okay.
Yeah, you can just go to that. You can easily. That is very easy. Easily you can do. Once you got that point. Once you will get that point.
So, could you give me any hints?
So actually, for this question, what you have to find that t exactly t expression and then compare. what is that in this question. Let me,
Okay.
I was to tell you the exact on week 6, one session I took, the first session I think itself, Friday's session. That on one session I took, I forgot the date. Today's 11, I think. Sorry, 11 I took the session. And that I totally how to find exactly T. So whatever you can do, let me tell you the brief as a hint. If I want to tell you the hint. So each time you have to find the T and then compare, because you have these images, no? This T of u, v is equal to 0, u is
Yes.
given, v is given, w is given. So each time you have to find the exact expression of T and then compare, okay, it is going to be a linear transformation like that or no. Similarly for others also, you have images, you have to check, and like here, whatever you did to find the exact T, how to find exactly, you just go
Equations.
the options wise, but there is a process to find exact
Yes,
T.
I process by standard basis.
Yes, correct. So similar process you can go and compare here. That's the here.
Okay. So question number 7, sir.
Okay. Yes, the question number 7. Each question you're asking. Okay.
In question number 7, option 1, and I have doubt option 1 and option 3. In option 3, I didn't understand T0T. What is the meaning of that?
T0T, option 3. T0 means this is just a
option
composition. 3. This is tells you a composition. So this tells you a composition word. Okay. And for option 1,
yes, in option 1, could you discuss the option 1?
If the identity matrix of order 2 is a matrix representation of this one with respect to a standard and for domain and codomain for both, it is also the matrix representation of T with respect to any other basis
as different, then matrix will be different. So here is said that on basis are different, then matrix should be same. How it is true?
So is this option is true?
Yes.
Yeah, actually there is a possibility, not exactly for the standard ordered basis. Not
okay, but in general that is not
exactly. In general it is not true, but yeah, it is saying if there is an identity matrix, there is a possibility to get the exact identity matrix with the different order basis. No, not in general. It is
in always, general that is not.
It is always possible.
How, sir?
Yeah, actually it is
Could you
how see how I am saying, if you have T of x is equal to suppose some yx, okay, so see if you the ordered basis for the matrix standard ordered basic, whatever you will get for this system of, actually this can be shown, okay. With respect to domain coding, then it is also the matrix representative of any other basis beta.
So this are given one example when we are changing the basis, then matrix also change. So in this question, that is in this question asks different.
In this question, yeah, it is saying to be there is another basis which have also the same matrix written. Matrix of T with respect to any other basis, means asking to be there is another basis, let's say beta, not
another
another basis, means maybe not necessary those are the standard order basis. Yeah, actually there is a possibility
Okay, sir. Okay. Another message that is that might be true.
I have one question. What is T0T? Once again, you just mentioned that. I missed that.
Composition.
Composition means, okay.
Could you solve option 3?
Composition means T of T, suppose xy is given, it means T of xy. Our T is from R2 to R2.
Okay, transformation of a transformation is what it is.
Transformation of a transformation.
Okay.
Okay. So I hope is it clear now? Of T.
Yes. Yes. Question number 8. Could you?
This is you need to be like
Okay. That is already solved. Yeah, that is already solved in solve with us. There are given in hint. So okay, 6.2.
Okay, so okay, let's do quickly maybe. So you just note it or just okay 6.2 which question?
Question number 1, option 1 and 3.
Option 1 and 3.
Yes, there are two kernel. So when we add those, when we are getting two vectors, that is satisfy kernel. So when we add them, that will be satisfy kernel. I can understand this.
Actually, you know, kernel is a subspace, no?
Yes, subspace.
So what is the use of subspace then? If you add two vector, it will go in that vector, no? This is the definition of subspace.
Okay.
Question number 3. It is option 3.
8. Okay. Question number 6 and 2. Question number 8.
Question number 8. Okay. This one. This one.
Hello, sir.
This question. Okay. So what is doubt here?
Question 8. Yes, sir. Question 8. Yes. In this question, I cannot get a correct answer. Question. Could you explain question option 4?
There does not exist any isomorphism between V and W.
Yes, there is a two possibility. So there is a two when there is a that is not a 1-to-1 or on-to, that will be not isomorphism. So option 4 will be true.
So asking there is it may exist, it may not also. So what is what is the dimension of this V?
Dimension of V, I think dimensions of V, that is a 3, I think.
No, why it is 3? Dimension of V is 2. Dimension of V
is B 2. Yes. 2 independent.
You have 2 independent variable. Why check?
Yes.
And dimension of W is?
W is, that is also 2.
That is also 2. Z and Y work as independent.
Yes.
So dimension of 2 is 2.
Yes.
Sorry, V is 2. Dimension of W is 2. So what do you think if 2 vector spaces have same dimension? So may have isomorphism or not?
Yes.
May have.
But
actually,
yes. But when you are there is another option. Choose option number 1. That is correct. So when you are option number 1, there is one independent variable. That is means nullity is 1.
Okay. You have
nullity is 1. So nullity 1 means that is not.
Again the same thing may happen. As you put equal to 0, you will get y is equal to 0. Once you will get y is equal to 0,
same thing.
Then you can check there. You have to take vectors. Yeah, same thing as previous one happened. So please be careful with that.
Okay, sir.
Yeah.
Okay, so let's move on. Question 6.3.
Oh, how many questions you have? Okay. This is the last one, I think.
That's the question, sir.
Sir, I just wanted to ask one question
Yes.
from graded assignment 6.
Okay, graded assignment 6. Yeah, yeah. Okay, just 1 minute.
Yeah.
I will. Yeah, just your
Question number
question.
6.
Yeah.
Just 1
Okay, sir.
minute.
Okay, sir.
The time is okay. This which question number?
Sir, I can tell.
Divya.
Yeah, question 5, statement 3.
Question 5.
Statement 3. Question 5. 5. Question 5.
This one. Question statement 3. Okay.
Yeah.
This T is a linear transformation with this one. Expression is given. Is a basis. Okay. Then the basis is this basis a image space? Okay.
How do we check that?
Okay. So is a basis of his image space. Okay, so we have this expression, okay, and this is going to image of basis. How do we check? Okay, image space.
The solution is already given.
Solution is already given. What is the solution? Okay, what is the quick way to? Just 1 minute. Let me see that. Supplementary content. Graded solution. Yeah, actually, there is a. I am thinking there is a quick way exactly to that. Whatever the process when can be done, but is there a quick way exactly we can do? Let's see that what is in the solution PDF itself. One, two, three. Statement 3 is there. Okay, image is this represented like this. Okay, this way and this. You can check that the set is okay. Yeah. Are you getting no? How it's solved? Divya?
If you could scroll down till here, we've just found sort of like the images of the bases, if I'm not wrong.
Actually, what is written here? See, this set is written as this form in this form.
Yeah,
This,
yeah.
okay.
Yeah.
Now you can take as x as a common, y as a common. I mean, common in the sense out, y, z as common. So these vectors, now whatever you have, actually this set, how it is written, this set is linear combination of these vectors. It is written like that. It is, if it is linear combination of these vectors, so now if this image space is the linear combination written as the linear combination means this vectors of image space is linear combination of these vectors, means in the separate form this can be written as a span of this thing, right? Now if this is a span, only remain to check is these are linearly independent or dependent.
Yeah, but we are already given 3 different vectors just given
different
below,
vector,
which we have to check whether they are the basis. This I understood. This you can obtain.
So what it mean that you got that the image dimension of image space is 3. Once you got that, once you check, okay. Now check whether these vectors are dependent or independent.
Okay, so first we have to check whether they're linearly independent. Okay, that will be through row reduction. So that is done.
Row reduction, you got that. Okay.
Yeah.
This is going to be independent. As here it is, whatever given vector is given, you got it. Okay, these vectors are linearly independent.
Yes.
Using the row reduction. Okay.
Yeah. And it has a rank of 3. No,
so
it has.
Because of this 0, 0, don't worry. This 0, 0 is just remove that vector, I think. Okay, no, it's, okay, no, this is written as
there are 3
column
variables.
wise. Sorry, in column wise it is written.
Yeah,
okay,
3
so you
columns.
got this. It have dimension is 3.
Yeah, so it can possibly be a basis.
So it can be a basis, but remain to that vectors are subset of that vectors are belongs to that image or not. That is we want to check.
Yeah.
So what is he? He just took the this one. Okay, T of image is this. So B is going to subset of image span is, but both have the same dimension. No, it's fine. Okay.
But how do we come to these terms? I mean, how do you arrive at these left-hand side vectors?
So what is the given thing? Okay, what is the thing now? Okay, you got that. Okay, these vectors are independent now. Okay, once you got using the row reduction, you got these vectors are independent. So how do we sure that these images, not these vectors are belongs to image or not?
Yeah.
So what is the process then? How we will do this?
Is it from going reverse from the transformation expression?
Yeah. From the reverse, you can go back to that. Correct. Using that expression, you can go back.
Alternatively, can we find the standard basis for R3? I mean, for the domain and the codomain, find its images and see if that image can be expressed in terms of these 3 vectors. Can we do that?
Actually, you can do it. Actually, this can be done also. See, finding the inverse of it will be more better once you find this basis. Okay. So check that is these vectors are written as the linear combination of these vector or not. That's all.
Yeah. So we solve for that. We solve for those
you can
A,
solve
B,
for
C.
that in exactly. Yeah, correct. This
which
is
will
also
be a combination of
or not. Yeah, correct. This will also work.
One of them. You can just take only one. Yeah. I mean, like for example, you can take 2, 0, 0. So a combination of these 3, a combination of these B would give us 2, 0, 0, 0 or not. Something like that.
As a linear combination of these one. This will work. Yeah. One by one you have.
So first we must prove it's linearly independent. It has the same dimension, and then we have to. Third thing, we have to prove that it is. If one of the images of the standard basis will be actually a combination of this.
I have a question on this. If you're okay, I have a question. Can you scroll down below, please?
Okay.
The screen is frozen for me. Yeah, all columns are non-zero. When you say that, how is it that? Can you scroll up a little? I'm referring to where you are declaring that this set is also independent. Columns are non-zero, hence independent is what you.
All columns are non-zero.
Yeah.
So, actually, this is these columns are non-zero, and we wrote our vector in column wise.
Column wise. Okay.
Column wise, and you said, okay, this vector is written in this vector. So what it means that these 3 vector only means this for that. Okay, if n of is used here, how you will generate this? No, you will not able to generate. So this says that okay, these columns are non-zero. R3 columns are non-zero.
I'm not sure if the problem is at my end, but the screen has not moved, and also your voice is not very clear.
Oh, my voice is clear or not? No.
Now it is. Now it is clear to me. Earlier it was not, and the screen was also locked on something else.
Okay. Yeah. So once you got, see your vector, here the vectors are written in column wise.
Okay.
Now once these vectors are written in column wise, you did the row reduction. Okay. When you did row reduction, these columns you can see, if suppose here is non-zero here, sorry, zero vector. Once you got zero vector, so what it means? This vector means this vector can be generated these two, na? Because here, right? So, but here you got one. So that means these three vectors is linearly independent. That's the mean. That's why here in all columns are non-zero columns. And this says, okay, these three vectors are going to be linearly independent.
As long as the pivot elements exist, I'm okay. That is what I can infer it as. Okay, and the last row being 0, 0, 0, that's by definition it is 0, 0, 0 as far as the question itself is concerned. That's the reason I don't really worry about that.
But yeah, but infer is from the column. That's why it may be you got the confusion. But yeah, once check, suppose you are assuming to 0, this means this column can be generated these two, using these two. Means here it will infer to here this vector can be generated these two, but it is not here 0, it is 1 here. So this infers that these vectors are going to be independent.
Okay. Thank you.
Thank you, sir.
Yeah. So that's the one thing. Let's do quickly the last one. It's going to be more than 3 hours. So which activity? 6.3?
Yes. 6.3.
Okay.
Question number 6.
Question number 6. Okay, this one.
Yes.
So
yes.
Distinct solution. What will be the maximum value of the rank of?
Yes.
Yeah,
so
what it says,
maximum value, that is a written. Yes, I did not understand it.
No, actually this says that you have two independent. What it means is, okay, so you have this one. It says that this equation have two solution. It means what? T of V1 is equal to 0 and T of V2 is equal to also 0. T of V1 is equal to 0. T of V2 is equal to 0. So that means you have non-zero kernel. Once you have kernel, you can use the row rank nullity and can get the rank of and or maximum.
Got it, sir. So I didn't understand that thing. B1 not equals to B2. Okay, sir.
So, sir, here
question number
since nullity is greater than 0, then rank maximum it can take is, how would we know?
How would we know? Because rank is written as dimension of the domain. Now
Sorry, sir.
Rank can be written. Rank is actually dimension of the domain V minus
rank plus nullity is equal to 4.
Yes.
Okay, nullity is more than 0. That means at minimum it will be 1. That means 4 minus 1 is 3.
So rank can be only at most 3.
No, it can be 3, 2, or 1 also. It can be.
Yeah, so maximum is 3.
It can be.
Yeah, maximum. Yeah.
Correct. That's the process. Okay, so in this
number 10.
Last question, sir. Last question. Okay, this.
Thank you very much. I will take leave now. Thank you. Bye.
You made it. Let me end the session. Yeah, which question number? This one. This is the last one.
10. Yes.
10th. Which option?
10th, 1 and 4. 1 and 4.
Okay. This that is equal to kernel. And the fourth one is there is possible. The fourth one is that linear transform are linearly independent, then V1 is equal to also are linearly independent.
So how do I conclude that?
Okay. So Okay,
So
I'm
could you
giving a
explain
simple
question?
example.
After question 1, can a
Yeah, you
kernel
can.
equals to image? How is it possible?
How this image equal to exactly the image equal to the kernel T? Image space image equal to.
That is only possible when that is a isomorphism.
No, it is not going to be an isomorphism.
Okay, could you explain? First, could you explain how to image equals to kernel?
To get exact image and is going to isomorphism.
Actually, sir, your voice is breaking, so that's why I didn't understand properly. Hello, sir.
You are in this. Hello.
Yes, I am on Discourse. I will be posted it. Okay, sir. Hello, sir. Hello. Sorry, got lost. Hello, sir. Hello, sir.
Hello, am I audible now?
Yes, you're audible. Sir, I am on Discourse, so I will post that question on that.
Yeah, just post on Discord. Yeah, I will post both.
Okay, sir. Okay, thanks, sir.
No. Yeah. So actually, it is going to be more time, and also I have internet to I'm facing maybe because of that my voice is facing breaking. So let's end the session. I will post in Discord.